Check, check, 1, 2. Check, check. Oh, yeah. Yeah.
So you have like two views?
Yeah. I can show you how I did it later.
Check.
Test, test, test. Alrighty. Just a note, we will be starting in about a minute. I know it's a very short break from the other session, so I do apologize for that. Go for it. All right, we're already a minute off, so I'm going to get started with the introductions, and hopefully everyone will wander in here. Good morning, everyone. My name is Jason Anderson. I'll be emceeing this session for the rest of the day. Thank you all. Again, we do apologize for the quick turnover from the other session. Just going to be helping with the schedule, so thank you all for your understanding. I hope you really get a quick snack. Thank you all to the attendees, both in person and virtual, for attending today. Again, main introduction was this morning. We're already running for time, so I'm going to go very quickly for this. As I said, I'm Jason Anderson, Bachelor's of Meteorology from State University of New York, Oneonta. I've been in the weather field about 17, 18 years, which is terrifying when I think about it. Spent about 15 years in the commercial weather sector, building global weather centers, building a startup working on weather and urban scale modeling in the UAS, UAV sector. And now I have the pleasure of working at NWS in the Office of Science Technology Integration, really working across our air quality, S2S, SFS, and HFIB programs, and trying to just bring, innovation, improve our modeling, advance the mission of the United States, and all of the mission to protect our people, the economic security, and just make sure people get home and have their home at night. So that's enough about me. Again, my role as student MC, yes, I am reading the script. It's here to just help us stay on time. I may need to give our speakers some gentle reminders as we move on, just to make sure that we have enough time and respect for everyone else. We also want to leave time for questions, everyone in person and virtually. So that will be my main role for today. No other questions or anything. Hopefully my next speaker is walking in here any second. Trying to see if we can find VJ. Yeah. Gonna have somebody go find our next. Oh, there he is. All right. asking ye shall receive. Oh, I should have gone through this. That's me. Again, we're live streaming. Schedule for today will be going till about 4:30. We're going to have some speakers here until lunchtime. After lunch, we'll come back and do an introduction to DA, AI/ML. We'll start talking about academic research that benefits NOAA. Again, another break. And then I think the really important part of this session for our students will really be, how do I get my foot in the door at NOAA? What are the resources of getting into the NOAA? What do I need to know? What are the skill sets I need? What are we looking for? And then, effective ways to network. One thing I'll say about my experience is Onion is a very small college. It's not very well known in the weather world, but we've produced directors of the National Weather Service, Air Force colonels that have gone in and actually been meteorologists and then helped build Afghan Army and other missions around global security. We build real fundamentals, but they don't really know how to get into this world. And that happens at a lot of the colleges, even the bigger ones. And so my real mission in my career has been to go out there and try to help professional, young Mets, graduating bachelor's, master's, whatever. How do I get started? What are the skills I need that I didn't learn in college or I need to hone in on to really get that first job? And so that's something I've really tried to do in my mission, whether commercially or in the government. So I think that'll be very important for all of you. And then we'll adjourn roughly around 4:30. Again, please connect with us on Slido, X, Instagram. Here are the QR codes. Participant guide is available. Wi-Fi if you need it. There's no password. Just hit UCAR Visitor. I think that's it for me. All right. Get this train back on track. It's my pleasure right now to introduce Vijay Talapraga from NWS. He heads NCEP and EMC. Vijay is going to be talking to us for the next hour. Vijay, please come on up.
Thank you, Jason. Good morning, everybody. I hope you are having a good meeting so far. And probably my talk is the longest talk for this conference, if I'm not mistaken. But I'll be talking about operational models and how we organize ourselves in terms of providing the necessary forecast guidance for all weather service applications that connects pretty much all sectors that depend on the forecast information. So I represent the Environmental Modeling Center, which will very soon become the Modeling and Development Center as part of the reorganization that we are going through. And so the goal here is to give you an overview of the center, as well as some of the activities that we do, and I'll also share some of the challenges that we are going through. Just to give you, to introduce the EMC, EMC is the premier institute for developing and managing operational models for National Weather Service in NOAA. This is our current organizational chart. We have the pleasure of having both the acting director and acting deputy director here in this meeting. So you will hear from Daryl later on about the data assimilation and AI/ML. So we have three major branches. One is the modeling and data assimilation branch. The other two are verification and engineering and implementation branches. Under the modeling and data assimilation, that's where the major model development activities happen. Have three different distinct groups. One is the data assimilation group that takes care of observation processing, as well as data assimilation, creating analysis, and provide initial and boundary conditions for our models. Model physics is essential. These are the people who develop physical parameterization schemes to represent the processes that govern the atmospheric and other Earth system component features. And then the model dynamics and coupling. This is another group that connects. This is the primary focus of this group is the UFS. The Unified Forecast System is a fully coupled model, and we focus on not only connecting the physics and dynamics within the atmospheric model, as you probably heard about that yesterday, and you will hear more about the coupling from Hendrik after me. But this group also caters to all Earth system component coupling that provides the basis for our NWP models. And our sister organization from OSTI is the meteorological development laboratory that stays within the headquarters, and that's the one that's aligned with EMC now. These also have 4 divisions. One is the statistical modeling. What they do is the development of products using the numerical models that we develop and provide forecasts. They are the ones that developed something called National Blend of Models. That is an ensemble technique that combines different forecast outputs to create the best possible outcome. And also bias corrections based on the past history. The Digital Forecast Services Division that provides the visualization as well as the verification tools. Decision Support Division that is mostly focused on individual sectors like aviation and storm surge. And the last one is the Weather Information and Applications Division. So technically they are the users of the model output and connect to our user base. That's how these 2 organizations were working, and now we are merging. The Modeling and Development Center will expertly execute across the value chain of development and operational implementations. So the focus is on the life cycle of the model development from observations all the way to verification and validation. The decision support services, the DSS, they are critical for our stakeholders, include data visualization, tools, data delivery, improved display of our products, both interactive and static, and also direct stakeholder engagement. We want to share the technical infrastructure that enables innovations like the AWIPs in the cloud, brings closer the requirements process, effectively looping the agile improvement cycle. So the MDC supports the full value chain from collecting observations all the way to decision support and application development for IDSS. This is the background of where we stand. We have about 200 plus people working on these models at Environmental Modeling Center, and another 60 or 70 for MDL. So the total would be about 300 people working on the critical developments that are needed for NWP, the numerical weather prediction. So what do we do, or why we do what we do? The purpose of operational modeling is to provide decision support, right? So in order to do that, we have to get the science right so that our forecasts will be relatively accurate, so that we can inform our stakeholders on the decisions that they can make. So the decisions will be anything between the forecast warnings and the impact-based decision supports. The actions that people will take are based on the information that we provide on a daily basis or on a regular cadence. Some of them updated every 15 minutes. Some of them are updated every 6 hours. Some of them are updated every day. So there are so many products that we develop that are catered to individual needs, and we wanted to support all sectors that depend on the information, the weather information or seasonal climate outlooks. All that information is provided by EMC. So we develop, improve, and monitor data assimilation systems and models for all components of the Earth system. The primary ones that we focus on are atmosphere, ocean, land surface, air quality, and sea ice, and so on and so forth. So this is an animation of a 3-kilometer global model, fully coupled, developed using the UFS that represents the Earth system interactions in a global sense. And so we have a capability today to produce very high resolution global models using UFS. The real challenge obviously is this cannot go into operations because it takes too long to run. It takes about 10 hours to produce 1-day forecast. And the operational requirement is 8 minutes per day or less. So there is an implicit understanding that all these models are dependent on the available HPC resources. So if HPC is not a limitation, we could probably run this model even at a higher resolution like a kilometer scale. So we have to be smart, we have to be balanced in terms of the resource availability and the scientific advancements in creating these applications. So if resources are not a constraint, we don't need multiple models. We could use one model to probably generate all the products and also do the ensembles using the same system. But unfortunately, we are not there yet in terms of operational capabilities to do. So we have to be creative in developing different distinct applications to focus on specific phenomena. And that's where the NSEP production suite comes into picture. The production suite is designed to cater to all the sectors that are listed at the bottom, from life and property all the way to environment. And the forecast products that we generate are from warnings, like the tornado or hurricane warnings watches, all the way to the guidance for seasonal, subseasonal outlooks. As you know, with time, the uncertainty increases in terms of forecast quality. So we have to really focus on providing the probabilistic information at those longer time scales. But the needs are for minutes all the way to months, prediction scales, depending on our customer needs. And so we started designing different applications. All these names that you're looking at in this graph are different modeling systems that we have been developing for the last several decades. Some of them explicitly for specific phenomena like hurricanes and waves and space weather and storm surge. But also some of them like the global forecast system, which is the centerpiece for all our models. We have the ensemble forecast system, the GAPS. They are all designed to provide the global solutions, but we also have the North American specific models that cater to short-range weather prediction at local scales. And other applications like our marine customers will get the global ocean waves, storm surge, coastal tsunamis, nearshore waves. All those products are specifically tailored for our marine applications. And the air quality, like the dispersion for smoke, as well as the air quality in terms of PM 2.5, ozone, so on and so forth. So there are so many avenues for scientific advancement that can impact operations. So operational model is not just weather forecasting, it has multiple facets to it. But the underlying challenge here, as you see this chart here, we have too many models. And each model has its unique ecosystem, unique community, unique tools that are used to develop those systems. And so they have grown probably unmanageable very quickly because continuously making advancements to all these models at the same time requires manpower, computing, resources, both human and financial, to maintain them. So that's the reason why we wanted to simplify this production suite using a more sophisticated forecast system that's now called the UFS. So all these little boxes that you're seeing here are individual models that are not necessarily sharing any components among themselves. So they're all independently maintained, but they're all connected. You can see all the connections, the arrows are touching each other. That means if you change something in the global forecast system, it almost affects everything. So you need to really invest in multiple developments, even though you're only touching one part of the system. So this became really hard to bring in new advancements, new research into operations quicker, like what we were anticipating. So the goal was to simplify the production suite using this UFS. Now you don't see any names of these models. They're all using the forecast cadence as the basis for applications, from nowcasting all the way to seasonal forecasts. There are still some applications like the hurricanes and the space weather and the water model. They're all still connected, but the goal was to provide a coupled ensemble as a final product that comes with a high fidelity reanalysis and the reforecast for forecast calibration. It also includes the unified data assimilation system, which you will hear later today. So the goal is to develop these global applications and regional applications to replace the entire production suite using the UFS. So if you look at it, you will hear more again from Hendrik later on, but in a nutshell, UFS is a collection of tools or components that can be shared by different applications. So the applications that you're seeing in the blue colored boxes, they are the ones that are for specific sectors, right? Like the GFS, the GEFs, the hurricane model, the space weather, the short range weather. All these are applications. They are trying to utilize similar or same components that are forming the basis for UFS, like the dynamical core is the FE3 right now, and we will very soon have MPAS as the second dynamical core. But the point is, we have a die-core to select, we have multiple physics suites to choose from, and you have a mediator that connects all these coupled models. They are system components like the chemistry, land, waves, ocean, sea ice, and also air quality, hydrology, coastal waves, storm surge. We also have connections to the statistical products that I was mentioning, the cryosphere marine applications, the coastal applications. All these can be designed using the same components. We don't need to reinvent the wheel every time we need to design a new application. The JEDI is the engine for data assimilation. You will hear that later today. I'm not going to talk about that. Workflow, obviously, is the one that allows you to run this model, both for research and for operations. So all this is unified now. It is a configurable system that can span from local to global domains for predictive timescales from minutes to months or years. And so that is the overarching goal for us, to move everything into this ecosystem so that you're not sacrificing the communities. If you are a wave community, you are part of the wave community, you can still develop your own niche without worrying about the rest of the components. And the system will take care of integrating those advancements into the applications through continuous integration, continuous delivery, the CI/CD pipeline, the code management protocols that were established to maintain the system. And the nightly regression tests, for instance, will ensure that any development that goes into any of these components is not breaking other people's work. So that is the kind of software management practice that allows us to maintain the integrity of the system while allowing the science to mature and advance and transition into operations. So many models that we run, all of them are now slowly transitioning into the UFS model. All the boxes in yellow color are UFS applications. And the anticipation is that by next year, we will have about 80% of all those models that you saw in the jigsaw puzzle will be converted into UFS-based systems to make our life relatively easy. So some of them are the air quality models, the hurricane models, the global chemistry and atmospheric forecast system, the new application for air quality, global air quality, the rapid refresh forecast system. This is the short range weather. We have the GFS and the GEFs, and also the seasonal forecast system, which is going to replace CFS very soon. We still have a few applications that are still in the process of migrating to UFS, but we will be completing them. So I'll focus a little bit on the global modeling and what we are doing in terms of the development priorities. And GFS version 17 is going to be the next big upgrade. Probably by end of next year, we will have the new model, which is going to be fully coupled. The current model runs at 13-kilometer resolution. And the goal is to put a 9-kilometer resolution model into operations next year with coupling to atmosphere, land, ocean, ice, and wave models. The data assimilation will include Marine JEDI, which is the data assimilation engine that connects the ocean and sea ice. A lot of physics advancements that are included in this. This is where most of the research comes into play, because physics is one of the most challenging area where a lot of uncertainties are there, and we can make huge improvements by improving the understanding of these processes and incorporating them into our models. So we are introducing a new land model called NOAA-MP. the planetary boundary layer, which is crucial for all near-surface processes, convection, gravity waves, and the microphysics will be, for the first time, double moment microphysics in global model. We have unstructured wave grids with a two-way coupling. That means wave model will influence the drag coefficients and momentum and heat exchange between the ocean waves and the atmosphere. The GEFS V13, which is an ensemble version of the GFS, which is run at a slightly coarser resolution. It's a 25-kilometer resolution, but the model uses exactly the same configuration as the GFS. So instead of two separate systems, we now have one system for deterministic. The same system is extended for probabilistic predictions. It uses the data analysis-based, data simulation-based ensemble perturbations for initial conditions, and also stochastic components for physics that will provide the parametric uncertainty that represents the physical process information that can vary within the model. This model runs out to 48 days to provide sub-seasonal or monthly forecasts. So you need calibration. So we are developing a 30-year reforecast data set to support the forecast calibration and training the products so that the bias corrections will help improve the prediction at the longer time scales. So both are planned to be in implementation by end of next year. They're being actively developed and tested right now. So the joint effort for data assimilation integration is another major initiative which is similar to what the UFS is, but for data assimilation. We are currently using something called GSI, the grid point statistical interpolation technique that was built in 2007. For the last 18 years, we're using that. But some of the codes probably were written before I even knew what meteorology is or what data assimilation is. So JEDI is a project within the Joint Center for Data Assimilation that modernizes all the software that goes into processing the observations, generating the ensemble components, as well as the background error covariances and all the information that you need within the data assimilation. And the goal was for JEDI to provide a software architecture that is model agnostic. That means you can use any model. You can put your own model there, and it will generate analysis for that particular infrastructure. Generic and portable so that you can run it on multiple platforms. Does not impose any specific methodologies. You can choose from various algorithms within the data assimilation. And also, once you know what kind of observation is brought in, you can share that information across different components as well as different organizations. So to look at more details in terms of how the data assimilation strategies were developed, you can go through those two documents that are listed here that provides the history, current status, as well as the next 10-year strategy. And you will hear a lot more on this later this afternoon from Daryl Kleist. What are we doing for the seasonal forecasts? This is another major global application that we need to pay attention to because a lot of activities that depend on information from the seasonal forecast, like the hurricane season outlook or the droughts and floods for the next season, whether it's going to be warmer or cooler. All this information comes from something called CFS in operations today. CFS is the climate forecast system, but that goes only out to 1-year prediction scale. And that was last upgraded in 2011, 14 years ago. So there is a very critical need for replacing the CFS with a new system, and the UFS is now allowing us to replace CFS with this UFS-based coupled model. The current model especially is very weak in predicting the MJO, the Madden-Julian oscillation, which is a kind of a climate indicator for activities that are connected to the convection. And so, you probably already heard about it, El Nino and Southern Oscillation, that gives an indication about the seasonal characteristics of temperature and precipitation. And then the maritime products like the SSTs in the tropical Pacific, above normal temperature forecasts, below normal temperature forecasts. All these can impact your decision making, and the current model has too many problems. So we are trying to address them through a very systematic development of this SFS, which is going to replace the CFS in the next year or two. It also needs a reanalysis and reforecast, so we are developing a low resolution reanalysis that goes with the reforecast data. And there is a beta version of the SFS that's already in the making and potentially will release the data on the model. The model is already available in the public, so you can access it. But the data also is going to be available for people to look at and evaluate. So from the global, let's switch focus to high resolution regional models. These are probably the most depended models for day-to-day activities. These provide very localized information at a very high resolution, at a very high cadence. So these are hourly updated systems that provide severe weather information out to 18 hours every day, every hour, and then out to 84 hours, out to every 6 hours. They are both deterministic and probabilistic so that you have the wide range of information. In the current operational setup, we have different models doing that information, providing that information. The NAM, the North American Mesoscale model, and the NAM-NES, you can see different grids for different domains. And then there is something called high resolution windows. They are also covering Alaska and the CONUS. And so we are now designing a new system based on UFS that covers the entire North American domain at a 3-kilometer resolution. So this is, I would say, one of the significant accomplishments from UFS point of view. The short-range weather is the most widely distributed application for the community. So currently it is based on the same dynamical core, the FE3, the finite volume CubeSphere limited area model. It has a hybrid 3D water simulation. 30 members provide ensemble-based data simulation background. It includes the smoke and dust, very similar to the HER. The RAP and HER are the two models that are used for this kind of short-range prediction in operations. They are mimicking those capabilities, except that it covers the entire North American domain. We just finished the field evaluation of the initial version of the rapid refresh forecast system, potential transition into operations by February 2026. So next time you meet at UIFCW, you will hear about operational implementation of this model. But we identified a lot of issues with FE3-based dynamical core that potentially has some limitations in terms of how this model is predicting or resolving convection, especially, particularly weakly forced convection during springtime. And the other modeling system, like the MPAS, has a better handle on those kind of situations. So the goal is to improve the science, and so the understanding and the common understanding among all the scientific model developers is to switch to the new dynamical core MPAS for high resolution limited area applications, at least initially, with the MPAS die-core. And we are actively working on that to integrate MPAS into UFS and also develop the next version of the RRFS v2, switching to MPAS die-core. We will also add other domains like the American Samoa, Micronesia. These are other areas that Weather Service has responsibility for. And we wanted to use the same UFS-based models to cover those regions as well. So it's a challenge, but the challenge comes with opportunities as well. Regional air quality. This is another UFS application that has gained a lot of traction in terms of how we predict the wildfires and the smoke and dust and the PM 2.5 that impacts almost everybody who goes outdoors. So this CMAC is a community model for air quality that's developed by EPA, I believe, and that is integrated into UFS using the same regional model like the RRFS, except that it is running at a 13-kilometer resolution It also combines 3 different domains, the CONUS domain, the Alaska domain, as well as the Hawaii domain, into one big North American domain. And some of the examples of this system producing the best PM 2.5 or wildfire emission products that are more realistic and more accurate than the predecessor using a different modeling system. So it has even more sophisticated features, like getting updated boundary conditions from the GEPS aerosol component, the global aerosols. It also has some bias corrections for ozone and particulate matter predictions, a new dust module that allows us to predict the dust impacts very accurately, and also some post-processing to give you more accurate prediction, both for anthropogenic and biological emissions or biogenic emissions. So it is one of the most successful air quality model that's run in operations. Hurricane models, another important and successful story of UFS. So HAPS, the Hurricane Analysis and Forecast System, is developed in collaboration with AOML, HRD in Miami, and also EMC as major contributors, and the GFDL helped developing the necessary components. And what you're seeing here is a moving nest that tracks the path of the hurricane. And the model is running at 1.8 kilometer resolution as of today. So this model, the outer domain is at about 5.4 kilometer resolution. The nest that is tracking the storm is at 1.8 kilometers. This is one example for Hurricane Helene. There are 2 lines, obviously. One is the blue and the forecasted track, and the other one is the predicted track, 5 days in advance, and very high fidelity forecast, very highly skillful. And you can see the holy grail here in terms of rapid intensity prediction. The model is able to predict accurately the rapid intensification and rapid weakening as the storm is evolving in the Gulf. So it was not possible a few years ago to predict the rapid intensification. Now we are at a place where we can confidently say that the models have reached some skill, not every time. I would say, I'll be lying if I say every single forecast is like that, but there are enough forecasts of this quality that the forecasters started believing and using that information in the decision-making process. So that is powered by UFS and the collaborations that the community has brought in terms of advancing the science from research into operations. So the first UFS coupled model, actually, this is the first UFS coupled model in operations. Back in 2023, it was first implemented and then quickly upgraded in 2024 with HAPS version 2, where we increased the horizontal resolution and replaced the HICOM model with the MOM6. MOM6 is the choice of ocean component in the UFS for global and regional applications. We now have other models like the Schism also available in the UFS for coastal applications, but MOM6 generally provides the high resolution capabilities for regional applications as well as the global. And the HAPS has the vortex initialization and, more importantly, the inner core data assimilation. When you have the hurricane hunters getting data collected and transmitted in real time, HAPS is the only model in the world that takes into account the tail Doppler radar data from the hurricane hunters, along with the drop zones and other flight level data, assimilated near the hurricane core in real time. So we are taking advantage of the real-time observations available both for actually ocean too, like the gliders and the sail drones. All the information that's collected during hurricanes is made, they made it to operational stream, assimilated in real time and used to predict these forecasts. The latest model that was implemented a couple of months ago is HAPS 2.1. We want to call it 2.1 not because we don't know how to number it, there is a reason behind it. We wanted to call the HAPS 3.0 with a fully cycled data assimilation under JEDI. That is still under development. So we are hoping that by next year we will be putting the HAPS 3.0 with the JEDI. But HAPS 2.1 is no less important in terms of its implementation. It addressed a lot of issues that we identified in 2024. It improves the track and intensity forecast substantially. And for Hurricane Erin, HAFS is the best model for track prediction and the intensity prediction, even better than the operational forecast from NHC. So the dynamical models can sometimes outperform the human forecasters. That is what the power of UFS is. And the HAFS is global. It's not just for North Atlantic. Everybody who is impacted by tropical cyclones in the globe are benefiting from the developments that we are doing here through UFS. Some of the nations already adopted them in their operational streams, like Taiwan uses it. India recently started using it. And there are other countries who use our products because we run for all basins, the Western Pacific, the Southern Hemisphere, the North Indian Ocean, all basins are covered. We produce at any given time up to 7 storms. That is the capability in operations. If there are more than 7 storms, probably we have to drop one of them, but never happened, or I would say only 3 or 4 times in the last 10 years where there are more than 7 storms at any given time. So based on that information, we are using our resources wisely to produce these products for our global tropical cyclones, which is widely received and appreciated by our partners. The new kid in the block is the Global Chemistry and Aerosol Forecast System. It's called GCAFS. The reason for separating the aerosol component from the global system is to provide better air quality information, air quality forecasts for the entire globe out to 5 days every day, and to give more emphasis on the tracers and assimilation of data sets from the newer satellites. All that is coming together, and to allow the development to rapidly progress, we are proposing this GCAPS that will be potentially implemented in April 2026. Fanglin Yang, who is sitting here, is leading that project with Barry Baker and Corey Martin providing support. And so this is a first step towards a comprehensive chemistry-based forecast and analysis system. And the reason why we wanted to separate aerosol system is also lies in the fact that the tracers are very expensive in terms of advecting them in our models. So the DICOR has to handle these tracers as if they are prognostic components like the wind and moisture and temperature. As you add more tracers, the model becomes even more expensive. And since the needs for the aerosol community are not tied to the weather community, we could separate those concerns. But again, the philosophy is to use or reuse the same components that I was showing earlier under the UFS to create this new forecast system that potentially can rapidly advance the predictions of aerosols for the global domain. Another new application that's coming into UFS is the regional wave prediction system. The current practice in operations is to have their own little domains for each weather forecast office along the coast of the US, to have their own domain, have their own wave model set up, and models are run at operations, but they are designed and forced using individual weather forecast offices. We wanted to combine all those weather forecast office domains into one single system. And so this is again, Hendrik Tolman here is the lead of design of such a system, along with Jessica Meischner, who is working at EMC to lead this project. This will alleviate a lot of issues, along with unifying all the grid generation aspects, full spectrum of wave parameters, for instance, not just the significant wave height. And particularly when significant weather events like the extratropical cyclones or the tropical cyclones are present, there is a continuity of information between one WFO and another WFO, consistent tracking of the wave systems for better guidance to the coastal threats and impacts. We also have some specific output that supports our customers. And so this is a very rapidly evolving, and hopefully in the next year or two, this will also be implemented in operations. And it uses the same WaveWatch 3, the UFS component, in designing the unstructured high-resolution grids for the coastal. This is how it looks like. It's a single large oceanic domain. It uses the WaveWatch 3 and framework for future coupling to address the coastal wave. So all these little boxes here in pink are the ones that are currently done independently. So it's a huge integration in terms of how a single system can address all WFO needs in a single domain. All right, the models are one end, but models only provide information that's not necessarily translatable for how people use them, right? So we have to post-process them. We have to provide products that can directly be used by our stakeholders. And also combine different models that produce similar output so that we have better information for the probabilistic guidance. So we have so many product systems that essentially depend on all these models that we run in operations, but to provide value-added products to our community. So some of them include the North American Ensemble Forecast System that not only takes advantage of our internal models, but also external models like Canadian models and Navy models. The North American Rapid Refresh Ensemble, that's going to be retired, so I'm not going to talk about that. There are trackers so that you know how the models are tracking these systems in real time. The precipitation analysis for high resolution information about the rainfall. The World Area Forecast System, that's for the aviation needs. And about a few operational websites and the FTP data and all that stuff. So we have all that information that also comes from our center. And the verification system, how do we do what we do? This is being constantly monitored so that we not only inform our developers on the needs or gaps, but also inform our stakeholders on how skillful our products are so that they have an understanding on what to use and what not to use and where to use and when not to use. And lastly, you will hear a lot more about AI/ML, and no talk is probably incomplete without that. So the future of operations, are we continuously dependent on physical models, or how do we take advantage of the emerging technologies? So the AI/ML is rapidly advancing, as many of you probably are already aware of, and NOAA has started this project EAGLE. EAGLE stands for Experimental AI-based Global and Limited Area Ensembles. Quite a fancy acronym. It's still experimental, but we will be implementing in another month, actually, in less than 2 months, we will have this EAGLE in operations. We won't call it EAGLE in operations, but it will be AI GFS and AI GEFS. They are the two products that will be added to our production suite. And the ML for NWP is not something new at EMC. It has a long history. 30 years ago, we were using neural networks for retrieving wind speeds from our satellite sensors. And there are so many other developments that were happening in terms of emulators for physics, or the wave models, or the rip currents, or so many products or features within our NWP systems that have taken advantage of the AI/ML techniques, but now we have a full self-contained models that can replace or augment our physical-based models. So we're using GraphCast as the basis for our new machine learning model. It's called Eagle Solo for deterministic and Eagle Flock or Eagle Ensemble for the ensemble system. And we have two different versions of it. One is a 13-level vertical resolution, another one 37 levels. They are all driven by GFS analysis. They produce 16-day forecasts 4 times a day at a quarter-degree resolution. And the GEFS is the same concept, except that it has 30-member ensembles. Some of the results are pretty impressive, I would say. The 500 millibar anomaly correlation for geopotential height is kind of a standard metric for global models that are widely used to measure the skill. And the black line is the operational GFS, higher the better. The red is the European Center model. Our machine learning models are based on GFS are catching up or exceeding the performance of the other international models pretty impressively. Statistically significant improvement for these verification scores. Tropical cyclones, significant reduction of errors in the Atlantic from the machine learning models. One of the drawbacks, obviously, is the intensity prediction. The GFS intensity prediction is in blue, and the red or green are the GraphCast based. They have more than twice the errors. That means they cannot predict the intensity of tropical cyclones, but the track they can easily outperform. So we are testing them in real time this year, and this is one of the examples of Hurricane Erin. All these light-colored blue lines are machine learning GEFS model ensembles. As I said, the intensity is a flat line. The model doesn't know whether the storm is intensifying or not. But the track forecasts are pretty reasonable, I would say. They are giving the kind of spread that we expect, although still under dispersive, but they are behaving as if they are coming from physical models. So there is increasing confidence in using these models for operational applications. So to conclude, we are doing a lot of activities in the AI/ML front, not yet operational, but we will be very quickly putting them into operations. The bias correction techniques are also built using ML, directly predicting observations without using any models or any data assimilation. This is called Ocelot, or DOP. You will hear more from Daryl later this afternoon. So we have generative AI for product development, software development. So many other aspects of it are being integrated into our production suite as we speak. So I will end my talk with one slide here that shows how complex our day-to-day life is. This is the wheel of pain. Not the physics wheel of pain that you probably have heard about, but this is the production suite dependencies. The center of the universe here is GFS. And GFS touches almost all these little boxes that you're seeing around. So if you think you can only change GFS and forget about everything, that's not possible. So our operators at NCO care for all these applications. All these need to sustain and provide similar or improved performance as we make improvements to any of the modeling system. So there are upstream dependencies as well as downstream dependencies. So that's what makes our life more exciting in terms of how we can connect these dots, make sure everything is in harmony, nothing breaks, and nothing unusual happens when we provide these products that are used for saving lives and property. So we take it very seriously, obviously. 99.9% reliability is our goal, and we achieved it for most of the time in terms of delivering our products with high quality. So this is the most exciting challenge as well as an opportunity in terms of how we integrate. Once the UFS takes over many of these applications, they become probably obvious that because we are checking on the dependencies implicitly, our life will become a little easier, hopefully, and we are looking forward to replacing many of these applications with UFS that helps us bring continuous advancements more rapidly. The challenges and risks, I showed them yesterday, and I'll repeat them a little bit here. Limited resources and limited expertise. That's where you guys come into picture here on the expertise side. You bring in your techniques, your tools, your knowledge into our arena, whether it's software engineering, cloud architecture, anything that connects the scientific community to the software engineering community definitely is a big plus. The workflows, they are going to become complex, and we need to wait to improve those so that we can easily run our models on different computing systems. And as probably you are already sensing it, the physical model advancements and the AI/ML model advancements I wouldn't necessarily call it competing, but complementing, but we still have limited resources, so we need to prioritize which ones to focus on. High resolution reanalysis is a critical need for training our ML models. We don't have that today. And a lot of people love our legacy systems. They don't want to move away from them. So it's very hard to remove something that goes into operations. That's something that we need to care for. And the modern software engineering practices like the CI/CD or DevSecOps for all applications is essential for R2O and T2O. So with that, I acknowledge all scientists and engineers who are working tirelessly. They are the heroes behind the screen. They're not probably getting enough recognition for all the work they do to help meet the mission for weather service to save lives and property and improve the economy and the prosperity of the nation. So thank you.
We were actually a little ahead, so we have about 10 minutes. We want to do some questions for VJ real quick. We have microphones over here to my right or your left. Come on up. Or if we have anything on Slido in the back, let us know.
Hello. I have two questions about the HAVS system. The first question, I noticed that when you were talking about HAVS 2.0, you mentioned improved inter-core data assimilation capabilities. You mentioned TDRs, dropsons, et cetera. I assume that those observations were still assimilated in HAVS 1.0, and yes. So I suppose I'm wondering like what improvements were involved there?
So the major improvement comes from the fact that in the absence of any such data, we have something called vortex initialization, right? So that provides the background, the first guess for how the vortex should look like. And then we add the data when it's available. Sometimes they don't agree, right? So because the observations are still limited in some sectors of the tropical cyclone, not necessarily covering or providing uniform coverage everywhere. So we have to make those assumptions in rebuilding the structure of the vortex and still retain the integrity of the three-dimensional structure. So that's an art as well as a science. So we do a lot of trial and error, essentially, in making sure there are no violations of, say, the gradient wind balance or the super gradient winds that should be present, or the tilt of the vortex that need to be preserved, particularly for sheared systems. So those are the improvements that we are building into our DA system that helps augment the vortex initialization with the data without discarding the data or without losing valuable information. So there are minor improvements, but still very important for representing the initial vortex.
Okay, excellent, thank you. Do you want to ask and then, okay. The other thing I was interested in, I saw there was a slide at some point on the first day about an experimental ensemble DA system for HAVS. I was wondering if you have any details about that at all. I'm curious if that's, is that being cycled over like a storm-centric domain? Yeah, right. And you know, what kind of system are you using?
So wonderful question. Actually, you know, our model, the HAVS, is relocatable. It's on demand. That means we position the grids where the storm is. And we're moving away from that concept to a basin scale model, which is fixed in the outer domain. We still have the moving nests, but the outer domain covers the entire Atlantic or sometimes even the Pacific too, or the Eastern Pacific. So the multiple nests can represent the simultaneous storms. We don't need to repeat the grid generation for every single storm. That is still experimental, but the question that you asked is related to that, because once you have a fixed domain, you can generate your own cycle system to continuously develop the background error covariances that can support the cycle system. And then when there is a storm, you add the inner core. You already have a high resolution analysis. You're just taking advantage of the background information. It is still possible to do that with the current system too, but it is limited by the life cycle of the storm. So, but as you can imagine, the large outer domain adds the cost to operations. And the concept of operations, when you have to do 7 storms at any given time across the globe, you don't have enough large-scale domain to do the cycling. So eventually, the goal is to put a tropical channel across the globe. That way, you can cover any storm anywhere and become part of the global forecast system rather than have your own halves. But that's in the future.
Very cool. Yeah, thanks. My research is like directly related to that, so I'd love to talk to you after.
Absolutely.
That's
Love to
cool.
hear that.
Thank you.
Yeah.
Anyone else? Still about 5 to 7 minutes.
If you don't ask me questions, I will start asking you questions. Anything online? Okay. Thank you. Thanks again for your patience. And if you have any other questions that you don't want to ask in front of everybody, come back and talk to me later. Thank you.
VJ, thank you so much. And I will say, I've only had a chance to work with VJ for 2 years, but I've learned so much from him. If you have a question, please don't be afraid to reach out to him. He's very available. He loves to talk about this stuff, and he loves to also sing the praises of the people underneath him getting all this work done. So please reach out to him. Wealth of knowledge. All right. A little hard to live up to that, but I'm sure our next speaker will handle that quite well. Happy to introduce my friend and colleague Hendrik Tolman, who's going to be taking us to school on UFS 101. We hear about UFS so much, and we're going to get on the ground floor. So introduction to UFS with Hendrik. Go ahead.
Thank you. How does that pointer work?
Just hold the button.
Okay, gotcha. So since I'm a little early, and since I had also some time had for you folks to ask us questions, or the other way around, just to add a little bit, since this is really a student session. So, VJ, stand up for a second. So how many people do you think work for the weather service? About 4,000 to 4,500 people. Of these 4,000 to 4,500 people, 22 are considered to be senior executives. These are the people that provide continuity from administration to administration. Of all these 22, these are typically the directors of centers. There are only 2 people in the senior executive range that do not have to run a center and do not have to run money. Why do I say that here? Is because the bigger picture of this specific session is about what do you do with your career? How do you get there? And so Vijay pointed out that the global model is the centerpiece of what we do. It is the National Weather Service, so in spite of the fact that we do 6-way coupled environmental modeling, we still have a focus on weather. Yet Vijay, his career went through hurricanes mostly, initially. My career as a civil engineer in the Weather Service went through wave modeling, most of it. Yet, because of the need of the diversity of the knowledge, the 2 of us ended up in this very unique situation and positions where you have authority without responsibility and have the best job in the world. So other things I kind of learned, I learned a few new things this conference already. I learned how to properly use Hendrik. That will be shaken, not stirred. I learned that there are people who can talk more than I can talk. That will be Vijay. And I learned that the things are so complex that even if you do a unified forecast system and you work on that thing, things change and there are so many things there. So I didn't want to correct you on one thing. So I have not been actively in wave modeling for the last 10 years. So the regional wave prediction system, I had no hand in that whatsoever. So that is really Jessica. So I know there is so much complexity. I make similar mistakes when I talk about things, and so it's good to correct it. So UFS, so about 10 years of work so far. And I could give you the geek talk about it, but I was wanting to go talk a little bit more about why we do it. And Vijay and I did not coordinate our slides because we don't need to, because we think the same anyhow. But with that, so bottom line up front, we really started talking UFS. I started talking in 2015, of all places, at an invited talk at the European Center. And then in 2016, at all places, at an invited talk in Australia at Cocker. So we've been doing this for about 10 years, and for the longest time, that was talking about ideas about how to do things better. But what Vijay showed already is that the train has left the station. We are really doing this, and I think Vijay was a little bit conservative in saying how much UFS we're doing, because you could make the argument that RTOFS is an RFS, a UFS-based system too, because it uses the same underlying UFS software for HICOM. So we try to not even, we try to be a little conservative in how we do this. And so the one thing that I could do here, and I had to think about how to do this presentation, is am I really talking about UFS, or am I talking about how you can get into the UFS? I'm going to talk about the basics and about the thoughts and the ideas and the support behind it, because it is very easy for anybody of us to go like, oh wait, I find a nice application on the UFS website, I'm going to run that and do some work with that. But that kind of misses the whole big picture. And so if you are expecting more of a talk about how to run the UFS and stuff like that, that's not here. Go to the EPIC website and talk to the EPIC people about that, because that's really designed for doing that. So the reason why this picture shows kind of twice today is not surprising. I think I have used these pictures at least 25 times in presentations, and I think Vijay is very close to that. And but it's kind of fun to look at this. The pictures both actually come from a roadmap and a vision document that we published a few years back. I'll give the references later to that. But there's other fun stuff to that. You know, if you can have good eyes, the picture on the left says courtesy Bill Apenta. He was the one who actually put that thing together. And I'll talk a little bit more how we got there. I call this thing the quilt. It's not a systematic design, it's a quilt. Why do we do that? How do we get there? Well, before our last weather service reorganization, most of the decisions on what we did in operations was made by people like Vijay for the hurricane, me for the waves, kind of independently. And so you end up with all kinds of neat solutions for niche problems. That means that if you look at that quilt figure on the left, there were 26 major modeling systems in that. And at one point, between the standalone regional models and the hurricane models, we used as much as 7 different die cores just for regional modeling. So how did we manage to get away from there? It actually started with reorganizing the weather service and saying we are going to be really based on the requirements first, then see what the requirements lead to in terms of the products that we need, and then figure out a technical solution. So the picture on the right here is really based on, okay, what are we required to produce so that NOAA weather service forecast can do their mission? And that came up with this layout, and the layout is pretty much still what we're working on. We're not quite there that everything is in a full ensemble at the same resolution and things like that. And there are things like tsunami that, due to the nature of the type of product, are going to be using other models, but are going to be completely standalone models because we never know when we're going to run them. And we have to run them on 5 minutes notice. And so this kind of thing, water model doesn't quite fit in because most of the problems that we are dealing with, you go from smaller to larger scale in time, you also have to go in space. So if you go if you go a week or two out, you have to do something global, otherwise it doesn't work. Yet our national water model is a national model, so it's not global. So it doesn't quite 100% fit as much in that as otherwise. But Vijay didn't show his famous rainbow diagram, how we get from left to right. But we are already from 26 on the left to 21 in the right side. And as soon as the RFS comes in, and as soon as we retire the older hurricane models, we have reduced the size of the production suite already by a factor 2. And so there is really progress there. And so I was telling you I was going to talk about the bigger picture, not about the advertising talk and stuff like that. This is a slide that Ricky Root actually originally started based on long discussions. Ricky was with me, the co-chairs of the steering committee for the UFS for many years. And so this is really sort of, this one slide tells you why we're doing UFS. And so the purpose of this is that we wanted, instead of being just weather service making its models, the number one critique we used to get as the weather service is that we were a not made here type of organization. We would not take your models. The reality of that was that 20, 30 years ago when we started the development, our weather service computer was in the top 5 of the biggest computers in the world. We were the only computer in the top 12 that was always on. All the other ones were switched on, see if it works, get the operating system working, run a test really quickly to see how fast the computer is, and then switch it off before it burns down. Our computer was running the 5th biggest computer in the world, and we were not able to get people in the computer, whoever wanted to go in there, because of the security issues that we had with the machine. And so we had to do our things by ourselves. And then we went to a situation that our computer was smaller, but the security level went up after 9/11. After 9/11, it became almost impossible for us to get people who did not work for the weather service onto our operational computer. And then one of the reasons why we want to go to a community approach, if I cannot bring my collaborator into my computer, I'll bring my software to my collaborator. So that is a real key issue of why we wanted to go to community, and we went a step further, community developed software. The other key thing there is to do operations and research with the same code. Looking at what Vijay was showing earlier, traditional, the GFS was the most advanced version of the model that we had. The GEFS used typically the previous development cycle of the GFS, and the CFS used an older cycle still. Now all these 3 models work off the same code base. There's no hierarchy. They're all equally modern. So that makes one big impact. Years ago, I had some suggestions for improving a model at the Hurricane Center. The Hurricane Center told me, no, we're not going to take this because you did this off the previous operational model. It's the only one I had access to. That's already 3 years old, so that meant that it was very hard for people to collaborate with us because they only had access to something that was already old for us. So this whole idea of having everybody works with the same thing changes that everybody can work with the most recent versions, makes a community possible. So governance changed too. When EMC was only running in charge of the operational system, when Vijay and I were earlier in our career, we would basically have a lot of authority on deciding what went into these boxes. Oh, wrong one. There we go. Yeah. What went in all these boxes, if it said wave, I had the authority to decide what was going on there. And so I was the benevolent dictator of these things, and we had to compete with the community that goes like, yes, my model is much better. Believe me. So from both sides, from the operational side, us having the beneficial, or the dictators on our side who could decide what to do, but also the community not really wanting to do a community vetted type of evidence-based decision making. Everybody had to come together, and we are a lot further with that right now. And so the other thing which is kind of interesting, if you look at how we designed the UFS from the beginning, we make a distinction between the software stack, so that is all the component models that were on the inside of the graphics, that the blue and red graphic that Vijay showed, and the applications that are built from that software stack. We want to have as small a software stack as possible, but the software stack, you can't measure whether you're better or not. You have to do that with an application. So the applications is where all the evidence-based decision making is coming. Then the other thing which is kind of interesting, it's the unified system. Early on, we had to talk a lot about this fact that unified is unified, it's not unitary. A lot of people thought that our goal was to go like the UK Met Office, to have a single unified model. The goal has always been for the UFS to have the smallest amount of software tools to cover our entire mission. And I'll come back a little later on what's in there. That does not mean the goal is to have one model. Those are two very different things. And so finally, the impact is we are doing different work very differently. We are talking way more with development people, and because we talk with them, we have more eyes on what we are doing, and we get way more input from the community to more rapidly go forward. So this is actually a fairly old graph. It's almost 5 years old. Very similar to one of the graphs that Vijay showed. The idea is just to show you about the fact that this still is a very complex system. But even 5 years ago, we already had 7 major organizations contributing to this, including a whole bunch of universities. And if you look over the top, oh, wrong button again. Although JEDI and UFS are treated a little bit separately, from a workflow perspective, we are integrating all these things together, and we do talk quite a bit about that. So it's always fun that you have a guy that is a good used car salesman, and I'm from a long and proud third-generation used car salesman also. It's nice for me to be able to say that, but why do we do this? And so actually there are a bunch of mandates that make us do the UFS. So in 2017, our NOAA Science Council, which is across all the NOAA line offices, had a working group to look at what the benefit would be from community modeling and things like that. And yeah, I was one of the chairs of that working group. Jason Link was the other chair. And we published a report on that, which is sort of a first step towards the UFS approach. It's also a paper in Nature. I'll give you the references later. Then in 16 and 17, we started writing a vision and a roadmap document where actually these two figures come from that Vijay used. And so we put that on hold for 2 years before we published it, because this was also when Neil Jacobs was working on getting EPIC in place, and we wanted to make sure that whatever we published on the UFS would not be orthogonal to what EPIC wanted to do. But that was finally finished and published in 2020. And why do I point to a specific publication here? There were the signatures of the directors of the Weather Service, the directors of the Ocean Service, the director of Nestis, and the director of OAR, all signed off explicitly on that vision. And so really that was the point where all of NOAA bought into the UFS. And then NOAA, for those of you who are not that familiar with how the government works, NOAA does not have something called an organic act. There is not a law that defines NOAA. NOAA was actually generated by Nixon with President Nixon with an executive order. And that means that we have administrative orders that are defined in NOAA that define the law of NOAA. And so we just published last year an administrative order on software governance and the public release policy. So We have a formal NOAA document that says that we are doing UFS effectively, although it's a little bit more complicated than that. And then we also published our first official NOAA modeling strategy in the last part of the previous administration, which is also completely UFS. But it's going further than that. In 2022, we had something called the Legend Act. And the Legend Act, I'll go through, and actually that was mostly for NOAA. Last year we got early this year we got the Share It Act, which is basically the Legend Act for the rest of the government. But that's kind of cool and cute for somebody like me who has been pushing this from a culture perspective. So the Legend Act is literally one of those beautiful acronyms. It's learning excellent and good examples from new developers. And it specifically is directed at NOAA. It talks about us having to be open source, except for when we see that our codes are old and we want to get rid of them anyhow. Or when we have, for instance, in our ocean models, we use classified military data for assimilation in our ocean models. We will not share that with the data itself. It is already mentioning, the first mention of, one of the earlier mentions of EPIC as being also defined in law. And it deals with both models and the data. And this is literally a law if you read this, and if you read the text on the right, which is actually a direct quote from that law. This is literally as close as it gets that there is a law that tells us to do the UFS. And it's kind of funny how this came about, because one of the people who was doing a lot of input to this specific law was Neil Jacobs. So it's kind of cool to be able to see that, that you start something from a science and engineering perspective. And it's actually so far right now that the UFS is something that the Weather Service has to do by law. So here are some of those references if you want to take a look at it. These are basically, so one of the ways of seeing that the UFS is mature or not is to see of whether or not there's actually peer-reviewed references and things like that. So the first two papers are the Nature paper and the report. That was the first formal look of NOAA at community modeling. And by the way, for as far as we've been able to trace down, this is the first time ever that any agency in the US government actually seriously and looked and published on what they wanted to do with community modeling and with open source and open science. Then those two reports, they were published in 2020, but they were written in 2017 and 2018. These are where we have the signatures of the leaders of all the line officers signing off on it, and this is also where some of the original graphs come out that we use. And then it's kind of cool to see that there's a series of 4 BAMS papers that are all around EPIC. So it's Neil Jacobs' paper from 2021 about why you do community modeling. Then you have Louis Itzolini, Rick Spinrad, and Craig McLean, who are all either NOAA administrator or senior scientists at that level, as well as Dorothy Koch and Bill Apenta. Bill actually unfortunately was a posthumous contributor to this paper, but that's all about why we do EPIC. And then Enrique Alves and me and a few others wrote a paper to show that we could accelerate improvement in operations enormously. The example of this is that the unstructured grid that we're using in the wave models was developed by a PhD student working for a German and a Taiwanese university. Once that work was done, the US Army Corps of Engineers helped him put it into WaveWatch. The Navy and the Corps of Engineers did some test runs with that on the Great Lakes. We picked it up, and 18 months later we had it in operations, and we went from a 2.5 kilometer resolution model to a 250 meter resolution model for the Great Lakes. And so that has been one of the sales points of why a UFS style approach, and then it works. And then I just published earlier in this year the fact that my experience with WaveWatch over 30 years, because I still can claim that WaveWatch became an open source model around the year 2000 and has been probably the longest lasting open source, open science model in the US government. And so it's kind of fun too. But these 4 letter papers in BAMS are really interesting too, if you want to learn a little bit more about the background, why we're doing it and why this is successful. So a little bit back to what actually the core differences are between that quilt picture and the UFS thing. And so I'm going to have a quiz at the end of it on the table on the right. And if you want to read this, poster 35 has a readable version of the table on the right. But so we make a distinction, like I said, when we talked about that first slide, about the software stack and about applications. So this is the software stack. This is roughly the models that go in there. And on the right side, the bigger boxes are either tools or atmosphere or land or ice or these kind of things. And so somebody asked me 2 years ago, so where is the UFS model? There is no the UFS model. The UFS is a software stack that you can configure in different ways. And so does this look simple to you? 27 community components in a software stack? No, it's not. And that is because the problems we are solving are complex. The old system, the quilt system, would be possibly an order of magnitude more tools that we had in there. So this is really simple compared to what we used to do, but it's complex because we're dealing with a complex problem. And if you look at it, if you look at the atmosphere side, CCPP is sort of on the interface of doing infrastructure and modeling. So that's the Common Community Physics Package. So that is the standardized interface between the die core and the physics in the model. So the fact that we have FE3 in there, that was us consolidating the global models and the regional models all on the same die core when we could. And then we said, okay, let's put impasse in there too. So is that contrary to UFS? No, it's not. For two reasons. The one reason is that we have shown by objective evidence that there are some issues with FE3 that we do not think we can fix. Actually, for truth in advertising, RRFS V1 is going in with FE3 because for the large majority of the applications, FE3 works really well, but it's specifically convective storms over the Midwest that we have problems with. The other reason why it's okay to have FE3 in impasse is because it's part of our mission to become and stay the best in the world. That means that it is okay to have an operational system in there as well as a potential next generation, so you can accelerate transition to the next generation. So we are very successful with consolidating in the atmosphere. We're very successful with consolidating in the wave model, but we're not. Because the wave model is very successful because it uses WaveWatch 3 everywhere, but WaveWatch 3 is not a model. It is a framework and a software stack. And we still have a lot of different options we use in there. So on the one side, very successful. On the other side, you're comparing apples and oranges, or as Dutch people would say, apples and pears. And then the ocean is where it really, the aspect of unified comes forward. For the deep ocean and for long-term forecasting, I need to have very conservative, cheap 3D ocean models. We use MOM for that. For the midterm forecasting in the ocean, we've been using HICOM for almost 20 years because we had such a good community with the Navy for doing that. And so we use two different ocean models that have similar capabilities, but we have very strong communities with both. So we started out with both. On the coast, for storm surges, you need the best application is a very high horizontal resolution depth integrated model. If you do water quality or navigation on the coast, you have to have a very high resolution unstructured grid 3D model. And so with that, there's not a single model in the world that does all these things at once. So just from a unified perspective, from covering the entire NOAA mission, I can argue that I need approximately 5 ocean models right now. And so you guys going into the science, fix that for me. But so this is the software stack, and if you look at the poster, the color coding, red of course shows that we are not quite there yet. The 3 columns go like, is it open source, is it open science, and does it have a community? And you can see that there are a few things that are not quite there yet, but from this we build applications. Or let me go first to So what does a component model, how do you get there? Well, typically, particularly one of our working groups comes to the conclusion that we need an extra model, or one with the working groups, one of the people who use the UFS. Then usually there is no real conflict with other groups because of this do no harm principle that we talked about a little earlier, what Vijay talked about. And then we're making these things UFS ready, basically because we want to make sure that it's open source, open science code management that's there. We want to make sure that it is wrapped in ESMF new OPSI to be able to do a coupled system. And then we not just want to put anything in the software stack, we want to have an application that we can measure it against. And then this works because of what Vijay said a little earlier, because there's do no harm, high level code management principle that we have on the software stack. And one of the things that we had to teach people early on, this is a coalition of the willing. UFS is not a funding source. It's not like, hey, I want to put something inside of the UFS and therefore, hey, NOAA pay for me. And so we have things in the UFS that NOAA doesn't use. And NOAA doesn't pay for its maintenance and for its upkeep either. So that's kind of fun. And then so from this software stack, if you take all the rows in here and just collapse them, these are just some examples of applications that have been built. I make a distinction between three, and again, this is also readable on the poster upstairs if you want to take a look at it. So the ones on the left are the epic releases up to last summer. The ones in the middle are operational UFS applications. The ones on the right are R&D and developmental things. And so what do you see here? There is still some red in there, so we're not all completely everywhere yet. If you particularly look at this block, these are the 8 different prototypes of the 6-way coupled system from left to right. And you can see from left to right, things get greener and red things are disappearing. And so that shows you that with our development work, we get closer and closer to it. You can also see that there are some things in the production suite still that there's only one little green box in there, and gray means that don't need this component at all. And so there are still some UFS components that are not coupled models. And but the whole idea of this is you see the complexity, you see that applications can be very different, you see that we are having clear progress in time. And to sort of mimic or to sort of summarize that, we're planning to make the production suite 70% leaner by getting rid of 70% of the large of the count of applications. Yeah. We are already at 23 with some of the progress that Vijay was going to show. We're close to 50 pretty soon. Community. Neil Jacobs tried to run the GFS on his supercomputer at Panasonic. It cost him about $15 million to get that done, and a year and a team of 6 people. The first UFS release of a coupled global ocean model, Neil Jacobs it took him a day on his Mac to get it to run. I thank you for the applause. And first time ever, in 23, National Science Foundation was willing to put research R&D money into operational systems. That has never happened in the 30 years before. Evidence-driven, it's a little bit too early to show whether we accelerate R2O a little bit, but the simple fact that the CFS V2 was developed over 5 years by a team of 6 people, and that we have more than 120 people actively collaborating on the SFS tells you how we've actually reached that thing. And then I already mentioned the planning, I already mentioned it a little earlier. And you've seen some of these plots because Vijay used them too, but the simple fact that you have a real hurricane model, a real coupled global model, and a real regional model that are either in operations or prototype for operations, and having reached that in about 5 years, essentially, is a pretty fantastic success story. And so next step, we need to talk about governance. Um, we are planning to get a UFS strategy document, at least in draft format, by the next UFS meeting. We're going to focus on the modernization of the software stack. I talked about that yesterday afternoon. And I actually do have a position paper, which is on that title there too. Starting to talk about the next generation coupling approaches, and then things like, okay, MPAS goes into the one-on forecast system, so on some time, I'm pretty sure people are going to take a look at see if it's better for other applications or not. And then it is applications, 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 and applications. And it is the thing that I avoided to talk about so I could stay within half an hour. If you really want to do something, it's epic, it's epic, it's epic. I don't think we have much time left, but.
I was going to say, we got 2 or 3 minutes. If you take a question or 2, you're quick.
I just adapted my talk to the other thing that I would like to suggest people who are early career. Don't be an introvert scientist, ask questions in public.
I do have a quick question about the software stack slide that you showed. I'm still trying to understand how all these different components work together. So so there were 3 different, there was like FV3 and MPAS listed for the atmospheric component. Is the idea that if I'm a forecaster and I want to run UFS, I can like configure it to use FV3 for everything except for Midwestern convective storms and then only use MPAS for that, or how does that?
The selection of the pieces of the software stack are at the application level. And so right now, it basically means that if you run a regional model, you have to select one atmosphere for the whole regional model.
Okay,
If you go, and this is getting into the nitty gritty about us wanting to start talking about coupling approaches different. So right now we're coupling these whole models for the whole domain to each other at the top level, leaving the models themselves individual. The National Water Model had done some work on designing their next generation model. They use something called the Basic Modeling Interface, where the National Water Model is going to be designed so that you can actually use a different hydrological model in a desert than in the forest. And this is one of the things that I hope will come out of a discussion about the next generation UFS that may be a capability to run different models or different component models over different domains, but not yet. This is something that is part of that coupling discussion that we need to start.
Okay, thank you.
Hendrik, thank you as always. He will be available throughout the rest of the week. Please go see him at his poster. Again, like VJ, a lot you can learn from him. I think at this point we're now ready for everyone's favorite session, lunch. No one told me what we're having for lunch though, so it's a mystery to me and everyone else. We'll meet back here at 1 o'clock. I'll do a 5-minute warning, 5 till. Other than that, thank you all. We'll see you in about an hour. We'll be getting started here in just a second. Just gonna let a few more people roll in person and online. All right, I think we're pretty good. All right, so to begin the next part of our session, I want to introduce our two speakers. We're going to be talking about an introduction to data assimilation. We'll start out with Daryl Kleiss, our Acting Deputy Director of EMC. Daryl?
So I'm glad I get the opportunity to talk about DA. So I made no assumptions about who knew what. Do any of you have any experience or have been exposed to data assimilation in the room? A little? All right, we're starting from zero. I'm assuming nothing. Get this to work. Yep, I got it.
Or we can use the clicker.
All right, so I'm sure most of you already realize that data assimilation is really important, particularly for numerical weather prediction. At a very high level, it's really just combining observations with model to produce initial conditions to then produce a forecast. And I'll talk a little bit about the process of how we do that. But as I mentioned, traditionally it's tied to a model. So data assimilation is fundamentally dependent upon the quality of the model that's producing the background. So if you use a really good model to combine with observations, you're going to get a better analysis and better forecast. Take it to the extreme case. If you have a perfect model, data assimilation doesn't have to do any work. Observations will bring no new value because the model is already perfect. So there's sort of a balance in terms of the quality of the observation and what you're combining it with. There's a whole host of algorithms available. There's some DA scientists in here. If you want details, talk to Joseph or some others and they can get into the weeds. Because you're the DA person I saw in the back of the room. So just to highlight, to reiterate the importance of data assimilation for the quality of forecast skill from numerical weather prediction perspective, this is an old graphic from a paper. I have the citation here. It's basically showing forecast skill at various lead times from day 3, 5, and 7, so top, middle, bottom. So obviously longer range forecasts have more skill, so skill's lower. And it's showing sort of two versions of running a data assimilation and numerical modeling system using the same observations. But the blue, the red, and the green are from a newer system, about a decade of development later, using the same observations, showing that the quality of the model and the simulation system is really important for extracting information from the observations to produce the initial conditions to produce a forecast. And this is a pretty significant leap. I forget the exact details, it's in here, but we're basically gaining about 1 day of lead time for every decade of development in terms of numerical predictive skill. And a lot of it is because of resolution computing, but also the science of extracting information from observations to inject into the initial conditions. So Vijay probably showed this before. One really important part of data assimilation is the model. Model is developing. This is an example of the UFS, the six-way coupled system. So this would be one piece of information we use to do data assimilation to combine with observations. The state space for this is pretty large. There's about 10 to the 8th elements. So we have a lot of grid points and variables to have to create initial conditions for. And what we do, oh no, my favorite thing.
No, wait a second, you got to load up a separate screen.
Oh.
Just give him a second.
How do I get back here? All right. That's what I get for touching things. Keep me away from buttons. What I'm going to show is an animation of the global observing system, and it's basically coverage of observations just within a 6-hour window. And this is actually now quite old. So what you can see, all the different types of observations we have available to combine with the model to produce initial conditions. You can see polar orbiting satellite tracks. The yellow over the conus is obviously aircraft, commercial aircraft. We have instrumentation for humidity and temperature. You see disks popping every once in a while from the geostationary satellites. Typically, most operational centers use atmospheric motion vectors derived from geostationary imagery. You can see the hourly synoptic METAR observations pop up every once in a while. So using all of this information within a 6-hour window to combine with the short-term forecast to produce one initial condition. And these things are not all always direct measurements of the model state variables themselves. For example, satellite C radiation. That's not a model prognostic variable, so we also have to figure out how to connect the observable to the model itself to produce the initial condition. All right, so we have about 10 to the 7th observations to combine to create initial conditions for 10 to the 8th state space approximately, using a variety of techniques. If I can get back to the slides, please. I'm not touching it, I'm not touching it, no touching. I'm trying. All right, so schematically, just putting to a graphic to what I just described. So we have past observations from within an assimilation window. We're combining with a model forecast to produce an initial condition. We then reinitialize the model to move it forward in time, and this entire thing is cyclical. So that we carry forward information in time through the model by combining the observations with the model itself. Here's one example. This is a pretty, I like this. It's from a book because it shows just a simple scalar example of ozone retrievals. So here we have observations derived from satellite. We're combining with the short-term forecast of ozone concentration to produce an analysis in the bottom. And there's lots of things we have to consider to do this, such as the air characteristics of the observations themselves, the air characteristics of the model forecast or the background, to combine it in an optimal way to create our best sense of the true state, which we actually never actually know. And if you're a math geek, this is how we do it. So fundamentally, there's dozens and dozens and dozens of algorithms. Data assimilation is basically just trying to answer K. We're basically using K in this set of equations to get the observations back to the model to produce the initial condition. All right, so you probably heard about JEDI this week already. We made a huge investment through an interagency collaboration to produce our next generation data assimilation infrastructure using the concept of basically trying to make it both model agnostic, but so the user only has to focus on the specific thing that they're doing development for. JEDI is designed to separate concerns as a variety of algorithms. It's model agnostic, although you do have to worry about connecting the interface to a model itself. There's lots of observations available. It's modular. Training is now available. There's a JEDI EDU. So we have both the Joint Center for Satellite Data Assimilation, look them up on their website. We also have the Consortium for Data Assimilation Cadre, who's deploying all kinds of training using JEDI as the mechanism. So it's generic code. It's eliminating duplication of development. It's been embraced by NOAA. Actually, the UK Met Office is a key partner and some other agencies within the US. So data assimilation is inherently transdisciplinary. There's no single set of skills that create a perfect DA candidate developer. You have to remain adaptive. You have to be a good engineer. Theory is great. If I went through and told you all the assumptions we have to make to get through that set of equations and then show you what we do in practice, you would probably have some cognitive dissonance and wonder how any of this even works. So it's all about compromise, especially when you're talking about applications of data assimilation for operations. We blow theory out of the water just to make things work. Diversity and experience is really important. I'm actually a meteorologist by training, but I spent most of my career doing software engineering and linear algebra, probability, and statistics. So there's lots of ways to plug into data assimilation. We're embracing modern development practices, including object-oriented programming, CI/CD, Agile. And the elephant in the room is, do we even need data assimilation anymore? So we're going to pivot here a little bit to talk to some introduction to AI/ML. And to just set the stage, we're thinking a lot about data-driven data assimilation, so using AI instead of traditional DA. And we have a reference that talks a little bit about this for how we're thinking about this. And integration of AI, both in terms of low-hanging fruit, so connecting to observations, the forward operators, background error, background, model error, emulation, and most importantly at all, we're starting to pursue these applications where we do data-driven prediction directly from observations to future observations. There's no model involved at all. There's no data assimilation involved at all. It's using observations in the training to produce an emulator of a prediction in the future. This is a really exciting development, although it's making some of us a little bit nervous about our future job security. So with that, I'm going to save questions to the end because I want to give time for Stephen to talk about AI. So we're going to pivot, and then I'll be here to answer questions on the bottom half.
Thank you, Dara. That was a perfect pivot. I'm honored now to introduce Mr. Stephen Head from a UK Met Office. Stephen and I actually just met a few minutes beforehand. I didn't even know you were going to be here in person. So it's an honor to have you here all the way. Thank you for making the trip to Boulder.
Super, thank you very much. It's wonderful to be here in Boulder in person and hear about all the fascinating developments going on. So I'm going to talk a little bit about AI and ML, kind of from the view of like how it is general innovation and how we're going to innovate sort of future developments through making best use of ML AI. So I'll give sort of a different perspective. I'm not giving a tutorial, I'm not going to tell you how to train a model. There's lots of materials out there. We've heard about many of the learning materials that Noah have already developed, so go and find out the technical details here. This is more of a broad overview. How can we make use of ML AI to deliver the next generation of value in weather and climate? So a little bit about myself. So I've recently started a new role at the Met Office, which is if I can remember it, Scientific Systems Lead for Data Science Guidance and Expertise, which is quite a mouthful and sounds very grand. Translated into English, my role is all about supporting the data science community of practice at the Met Office and the people working in this area, helping them work more effectively, more efficiently with the right tools and data and platforms, and helping people, because lots of people are coming into this area, like yourselves, from a broad range of backgrounds, finding them the sort of learning materials and that they need to get started effectively. And so coordinating that across teams. I'm not doing it all myself. So just a bit of terminology. What do we mean by data science? So here I'm using data science as a sort of broad term to include machine learning and artificial intelligence. And the reason I often use this term is because there's a lot of overlaps if you're creating a sort of pipeline for using machine learning and AI that overlaps with all our existing systems and ideally makes use of what we're already really good at in terms of tools and platforms. And there's an adage that I think Rob mentioned in the session yesterday that 80% of your time on ML projects is preparing data. So that's skills that are broadly used from other domains, and often what's really valuable there is understanding the data and that domain expertise. So I'm trying to emphasize those in using the term data science. And in my talk today, I'm really talking about kind of sort of hands-on technical work in terms of developing and using ML models. I'm not talking about using kind of off-the-shelf, Gemini, Copilot, ChatGPT type tools, but I'll mention some of that later on. This is more kind of getting into the nitty-gritty of that. What does that sort of work look like for you? Giving a sort of overview, how can we use data science for weather and climate? So one thing that's true of this field is a long history of producing lots of data and trying to make the best use of it. I often use this picture on, does this work? Oh, that's magical. This picture over here as an introduction. So this is something known as Fitzroy's barometers. The Met Office was founded 170 odd years ago by Admiral Fitzroy after a shipping disaster, sank a ship, and hundreds of lives were lost. And so they formed the Met Office. And one of the first things they did was they sent out these barometers to be installed in coastal communities around the UK, and then using the new sort of telegraph network, sent the observations back, and they could try and figure out what's going on. And my usual story is that we started by being data-centric and trying how to use that data, and data volumes have only grown somewhat since then. And we've been trying to keep up with techniques. And so AI/ML gives us an opportunity to possibly deal with these data volumes, and how to exploit them. There's also been lots of exciting developments, though, in recent years that have gone well ahead of what perhaps we might have thought we'd be 5 years ago, through things such as creating a data set that we can use to ingest, to drive weather models, there's something called Weather Bench, and then turning into the latest entirely AI/ML forecast models, so Pangu, GraphCast, AIFS from ECMWF. And then developing new tooling to make this easier to use. So we've heard about Anemoy at some of the sessions as a tool to kind of unify these things together to be able to make it really easy for people to use these tools in their research rather than having to be a sort of ML engineer to be able to do that. So there's lots of exciting developments there. The key thing to think about is where can we use AI/ML in the sort of in producing a weather forecast or weather products. So there's a sort of standard diagram we have at the Met Office for thinking about what's called the value chain, and thinking about where we can use AI and ML at all parts of that. So starting with observations, we've thought a lot about observations and how we include that. There's lots of areas we can do to use AI and ML there. So there's various things we can do to have sort of smart sensors where you have different sorts of observations. So, for example, can you extract useful information from webcams or citizen science, that sort of thing? Cleaning up data, quality control, finding bad observations to produce better quality observations, data sets, lots of opportunities there. Simulation is perhaps the headline-grabbing area at the moment. How can we produce weather and climate models that are entirely based on ML rather than the traditional sort of physics process-based models? And can they in fact go direct from observations? Something Darryl was mentioning, but that's sort of headline-grabbing area at the moment, those big models. But there's lots of other areas there as well, particularly thinking about processing analysis, so taking the output of a model, mapping from the sort of large global prognostic fields into particular things that people actually care about in terms of making decisions. As we've talked about earlier, that's ultimately the goal, is to help people make decisions, and kind of sort of large-scale variables need to be translated into what people actually need to know to make a decision. So there's lots of opportunities for learning those mappings from, often called from hazard to impact, using machine learning there. And then gradually creating a lot of bespoke products. So we, at the Met Office, for example, are in lots of sectors. So we work with the aviation sector, so they need a certain set of products. We, as well as we have the public forecast, but we work with, say, the energy sector to try and forecast, say, how much wind power is going to be generated or solar power. We work with supermarkets to help them with forecast demand. What's the other one I was thinking of? A bunch of particular sectors that's growing, and increasingly people are interested in understanding how weather and climate are going to affect their business, and so there's growing demand for creating these predictions that are helping the decision support, and we could potentially be much more agile and create these products much faster than we could in the past using data-driven techniques. So there's some kind of cool, some core tools and techniques that are kind of helping us make great advances in this area. So deep neural networks is an area that's sort of headline grabbing, and sort of two key architectures, as they're called in this area: GNNs, or graph neural networks. So GraphCast, AIFS, the models are part of Eagle. Those are the area of graph neural networks. Transformers, that's another area that came from language models. So things like GPT are based on transformers, and this was translated to use for images, and that then translated into weather. So something like Pangu uses transformers to do their forecasts. And this is part of the idea of a foundation model, not just a model that can predict one particular things, but as more general purpose. Again, given the huge costs of training models, inference is very cheap, but training is very expensive. The idea of training something for multiple purposes is going to be key in terms of being able to do this efficiently without completely blowing the budget. And part of that is going to be able to do it effectively at scale with huge numbers of GPUs and huge amounts of data. And how do we scale it up? So part of that is needing data sets that are ready to use, and also tools that mean that people that aren't sort of expert software engineers or machine learning engineers can bring their expertise. So the key thing here is being able to bring all that expertise in meteorology to defining the problem and understanding what we're actually trying to do, and therefore create good solutions. And that's part of what performance benchmarks is all about. The idea is actually the key challenge in using machine learning AI is actually defining what are you trying to achieve? What is a good model in this case? And that's where actually someone who's an expert in machine learning is not going to help. Someone who's an expert in meteorology needs to define that. How do we measure what is good? I think I've already covered those. So what does that look like in practice? So in general, there's a variety of different ways in which these work. So there's the sort of way that often people think about using machine learning is training a new model. So you get some data, you have to prepare it, and it often takes a lot of time. You train a model, and then you assess whether it's a good model or not, and you get a model out of that. But increasingly, actually, people working in this field are going to be looking at a workflow more like this, where you're actually using existing models in your research or operations to produce products. You're not creating new ones necessarily. And so here, you don't actually, what's exciting about this is that brings in a much broader range of expertise that can get involved in using ML/AI to do interesting and exciting things. Whether it's on the research side, using an ML model for your research, whatever that is, whether you're particularly interested in the weather itself or some sort of impact. We can bring in a range of expertise to make use of this much more dynamically, because you can generate these forecasts on demand much more quickly and cheaply. So there's lots of exciting potential there. And similarly, if you're serving customers, I was thinking of lots of things yesterday in the talk, for example, hearing about the sort of how cruise lines are using meteorology, how we could potentially create lots of exciting products that are bespoke in this area using the right data to do that. So that's really exciting. There's lots of areas in which you can get involved, and then using that sort of domain understanding in terms of meteorology to use ML and understand what are effective ways to use it as well as possible. But there's still a long way to go in that user journey, because there's some areas which we're good at. So we're good at like defining what we're trying to do as meteorologists, but there's still difficulties in actually then scaling up, training new models, using them. So there's lots of advances we've heard about how can make that a lot easier for the user, like yourself. And hopefully, because I think that's where the exciting things come in, where it's not just the sort of ML specialists using this anymore, but really bringing in people with the domain expertise and getting involved. Just sort of deal with the elephant in the room of sort of AI tools. I've not dealt with that, but there's also a lot of potential for accelerating the use of these through the use of off-the-shelf products to create these pipelines, to interact with data. And I think that's going to be a big part of the future, how we've accessed data in the past and used it, where it's often been quite difficult to find the right data, understand what's contained, and create these. Hopefully, with better interfaces to that, we can have a much more rapid sort of pipeline of developing new research and new products using data-driven techniques, and creating those without having to spend 10 years becoming an expert Fortran programmer first. Rather, you bring your knowledge of the domain and the particular research area, and then using that. So how can you get started is probably always the question for someone in this track. So there's lots and lots of exciting materials that have been mentioned already to get started, either kind of courses to do, but also there's lots of code and data out there for you to kind of get your hands dirty. I think that's the best way, is to just have a go for yourself. There's lots of guidance there to understand what's possible. And I've often found once you start doing these, it sparks lots of ideas from your own areas of expertise for how you can use this. And whereas probably 5 years ago, this was then difficult for someone who hadn't spent ages becoming an expert, now people across the Met Office we found have now been able to have a go themselves and that's created all sorts of exciting outputs and products. So this accelerating greatly as a result of this build-up of making things easier to use. And so yes, there's lots of ways to get started to use your domain knowledge of like, what are we actually trying to do? What exciting things can we do with data-driven techniques for weather and climate? So yeah, get stuck in.
Testing. There we go. Stephen, thank you so much for that. We've got about 7-8 minutes left for questions for both Stephen and Daryl. One of you guys want to take that mic? I'll give this to you. And questions, please.
Oh, did we shove him off? Oh, wait, there it is. Oh, okay, thanks. Yeah, great presentations. Ben Woods with the Weather Program Office. Question to both of you, but perhaps to Daryl a little more. High-performance computing can be a limited resource, as you know, with data assimilation, some of the projects we worked on. Would you see integrating the AI as a help with that limited resource, or will it be even harder moving forward with that resource? Thank you.
Yes is the answer. It's sort of a two-part question. So the promise of using data-driven components is sort of the real-time execution of things. So if you build an emulator of a model and plug that in, like the real-time execution, that's quite cheap. But the hidden cost is all of the training you have to do to produce that. So the total compute might be the same or more, but how you need the compute is going to be very different. You have to spend more time in the training and in the background to then the real-time prediction is going to be sort of a little bit different. The other caveat is how much GPU we need relative to do some of the AI stuff that we don't really have on some of our, at least within NOAA ecosystem, and we're starting to explore how to do that. So I had a laundry list of things within the DA problem where we're trying to bring AI in to help solve some problems. A lot of those are specifically targeting computational pain points in data assimilation. So whether it's reducing the cost of the prediction model, reducing the cost of the solver, that will also help accelerate sort of the development because the actual real-time cost of doing the research and development is going to go way down. Stephen, maybe you have other thoughts you want to add?
No, I think you summed it up that yes, the like executing day to day is cheaper, but you have to do the training. But hopefully, by working together, we can train. We don't have to create loads and loads of models. Once we've got one that works, then we can do that effectively and make use of it. And as we kind of build up these models that reduce the cost, then once you've got a lower cost model that you can use in development of other things, then that kind of gradually builds on that, and you can continue to bring costs down. But there'll definitely be also kind of a balance of bringing kind of using existing techniques in AI ML to find the best result, and what that looks like is very much an open question. And there's weather and climate is not the only demand though on AI ML resources, as we're well aware. And so it'll be interesting to see how those constraints in terms of availability of compute to do all the things we'd like to do, how that constrains what we do in future.
So very, I think, heavily related to the previous question, but I'm wondering if you guys foresee the use of machine learning weather models and forecasting as this kind of thing where they're trained once and then you just start, like forecasters start using them and then maybe they get updated or retrained like every once a year, or do you expect training to be like constantly happening all the time as new observations and new results come in? Like how often do you expect these machine learning models to be updated for forecasting use?
Well, I guess there's how often do I expect versus how often would I like to see, I guess. So obviously this is a whole new way of thinking. So at the moment we have, I think it's similar to what was described yesterday, sort of an operational suite that runs our operational models, and then when we developed, there's a long, something, the figure usually quoted as like 3 years from scientists like demonstrating a new technique is good to like it actually getting into the operational thing via a long sort of 6-month parallel suite process where it runs alongside it. And so that's the thing. So potentially there's an opportunity for that to be much more frequent, but also kind of not just having because the reason you do it like that is just because the cost is so huge of running that parallel suite alongside a whole operational suite. Whereas the cost of, you can run several suites in parallel if they're all AI ML, potentially. So there's a lot of opportunity, I think, for just having multiple cadences. So I think there will still be a sort of canonical, long-term release like you have for operating systems and so on. But I'd love to see it thinking really creatively about the sort of operations to research to operations kind of cycle of we have operational meteorologists looking all the time at where their weather busts and where things are going well and where they're not. And the cycle of getting that insight back into informing better models is really long. Can there be some much more automated system where every night we're using the latest insights to fine-tune something and seeing, and then you kind of have those the different versions of things running alongside it and real-time assessments sort of every day in terms of what's useful, and so a much faster cycle. But what does that look like? There's a lot of infrastructure to be put in place that's just not there at the moment to put those rapid advancements in front of operational people and then get the insights and retrain and making sure you've got the compute infrastructure. So I think there's a lot of exciting potential. So a lot of the moment, the thinking has been how do we kind of do a replacement that's much cheaper? But I think there's also a lot of scope for thinking how can we just do things that aren't possible at all at the moment, and that's what I'm excited about.
So I'm going to take my DA hat off and put my deputy hat back on. I agree with this. So there's probably going to be some paradigm where we have flagship global emulators or things like that have a fairly long time scale in terms of releases. Maybe it'll be quarterly, semi-annual, something like traditional NWP.
One thing that we can crack open though is the ability to build bespoke applications for particular users and sectors. Because they're so cheap from an operational cost footprint, we can build an agriculture model, or we can focus on a particular phenomena. Those kinds of things are going to start being deployed much more rapidly. So the sort of application space of emulators, I think, is going to explode, and that's going to have really, really sort of rapid cadence, because it's going to be either user or sector tailored, but sort of the traditional stuff is probably going to have a slightly longer cadence, sort of like traditional NWP.
I apologize. I know we've got more questions out there. We'll try to do them at the end here. Round of applause again for both Daryl and Stephen. Thank you both very much. Excellent. All right. Don't need two mics in front of me. I'll give you guys any blowback. It's my pleasure now to move into one of our first groups. We're going to take a little bit of a pivot here and kind of look at the academic research area and how does academic research kind of flow into NOAA and how does it benefit. And so with that, I want to introduce our session chair, Mr. Andrew Winters. And he'll be introducing the rest of our speakers. Andrew?
Thanks so much for having me. I'm Andrew Winters. I'm an assistant professor here at CU Boulder. It's my pleasure to lead this session focused on how academic research plugs in with NOAA. I think it really dovetails nicely with Hendrik's talk earlier about how UFS is this collaborative endeavor. And here I think is some great use cases from four really great speakers that'll focus on some of the ways that they're doing work within their groups to benefit NOAA and prediction within our Earth system. So with that, I'm happy to introduce our first speaker. Our first speaker is going to be Sen Chow, who's virtual. Sen is from the NOAA Cooperative Science Center in Atmospheric Sciences and Meteorology at Howard University. Sen, feel free to take it away from here.
Okay, thank you. Do you see my screen right now? I'm sharing my screen.
Yeah, we're just getting it up and running here.
We're just finishing the technical issues.
They're good?
Looks like we're seeing the presenter view.
Oh, presenter view. How? Let me see. How should I just do slideshow? Well, that's all I can do. Am I able to?
Yeah, do the swap displays if there's a swap. I think it was the drop-down menu there for display settings. If you go back to the display settings drop-down menu.
Which one is that? Here?
Launch the slideshow.
Yeah.
From the beginning.
Uh-huh.
And then in the top left, there's a display settings drop-down menu.
Yeah.
You should be able to swap the views if you click that button.
Is that this one?
Yep, that's perfect. Thank you.
Gosh, that's difficult. All right, thanks for the delay. Again, thanks for the opportunity. I wish I could be there, and it's teaching courses that basically make it difficult. But I want to shift the gear, basically just kind of give a different flavor in terms of to fulfill this section's topic. So I want to give you updates in terms of how actually more than 22 decades actually, in terms of how the efforts that at the university levels and then working with NOAA line offices that for this many years, then how far we could go, and then what achievements we have. Also moving down the road, what we are facing the challenges. Actually, I want to give updates. Oh, so here's basically what I'm going to present. Basically, a little bit history. For those of you who don't actually know much about NKSM or the Cooperative Science Center overall. And then also touch a little bit on the goals and objectives that NKSM we are aiming for. followed by the idea of combining the training and education, research and the education together, and then to fulfill that requirement for the future NOAA workforce and then global competitiveness. And with the update about current research project, and then summary with the challenges, opportunities. By all means, I forgot to mention that my research staff basically helped me on this slide deck, basically. All right. So for those of you actually don't know much about NKSM, basically we are one of the 4 NOAA collaborative science center in the nation. So NKSM, which is stand for NOAA Center for Atmospheric Sciences and Meteorology. And our mission basically is aligned with the National Weather Service. But actually, we actually work beyond that part of the effort in terms of all the three items I want. Again, I'm not going to read it, but you can actually see it. That pretty much cover overall from the weather to air quality, in terms of prediction, in terms of measurements. Also, one very important part of it, which is to integrate the research result into the IDSS, which is it's a big effort that in the past few years, impact-based decision support service. So that's actually what we've been aiming for. As you can see on this a few pictures around on the right, basically this is actually, I want to say that we are one of the few campuses really right inside downtown DC, and then the top picture basically that shows the rooftop, which we call it penthouse lab. Basically, you see Doppler wind lidar, accelerometer, and a bunch of other things over there. And then there's a far away on far side. There's actually urban net. For those of you know that the ARL Air Research Laboratory has the urban net right here in DC. So Howard University is actually right. Probably, I believe that's the second one set it up within the urban net. You can Google it online. And then the bottom picture basically shows that Beltsville campus, for those of you been there before, then you know that it's actually the test bed for several agencies over the open area that we can do a lot of things over there. Now, again, here's a few highlights that I want to talk about. Again, I'm not going to read it, but I just want to tell you that with this joint effort between NOAA APP office, NOAA Office of Education, as well as many of line researchers and staff at the NOAA line offices, that to this point, we have basically achieved quite a few things. Again, training students, especially the underrepresented group of students that we have been working with them and combining the research. And then also, again, feedback to how the training and research that align, which is a very important part of it, align with NOAA line offices, actually, especially we are right here in DC area. So it's actually more critically important to do so in order to really make this joint effort. So with that, I want to move on to a few projects, again, that currently to kind of give you a brief idea about what we are doing, that we are working with NOAA line offices right now. Now, the first one, which is, again, I put the name there, as you can see that in terms of how we want, as I mentioned, how we want to align ourselves. So the first one, which is the HAPS model, data simulation. I know the previous section talked about the DA. And again, we are part of this effort, and then also working with the cadre, which is the data simulation consortium, led by OU group. So again, two major efforts, actually, I want to say that. Again, as we are closer by ENC, we just had a meeting earlier this afternoon, basically, kind of monthly update in terms of what we do. Basically, just as most of you know, that we have two different workflow. One is the cadre workflow, the other one is the EMC, the HAPS workflow with the JEDI. And our role is actually sort of very interesting in terms of testing different capacity with the update JEDI workflow with the hubs model. This is just one of the effort basically telling you it's a case study for especially for Vero 2024 Hurricane Genesis that we are working on it. A lot of interesting in terms of how beyond the research part of it, it's actually how much we see that contribute to the operational point perspective in terms of how EMC could possibly use the result, or how we as a team can contribute to EMC and the HRD as well. So that's actually this project, especially what we are working on now. The other one, which is actually more working with NOAA OAR GSL. Again, the name says with Derek Turner, Dwayne, and Isadora basically we are working with them. The idea is basically more on the research side, really looking into how the high order turbines that we use the Raman LiDAR over the arm side in Oklahoma. As you can see the plot here, but again, just quickly summarize it. Using the Raman LiDAR data, looking into the quasi-stationary period of time in terms of how the boundary layer evolve through different calculation in terms of how try to quantify that convective mixing layer in terms of again the highlight, the two box here basically shows the ramp up time and then stationary time, how the behavior was that to verify that part of the effort. So that's basically, now bring the figure out here. So the preliminary result is actually looking into the ramp up in terms of the autocovariance method that we are basically be able to understand more about that part of the activity, as well as how we're going to, most of you remember the boundary layer book. There's the sub-range curve, which is the two-thirds of the scaling issue. So we are right now, which is again, it's an ongoing project right now, try to verify that two-thirds of the number, not necessarily as a fixed number there. So some result will be presented the next AMS meeting. Now, the other project, again, this is with the OSTI, National Weather Service OSTI, with Jack Hand. Well, he retired officially, second time, not too long ago, and Young-san as well, currently she's there. So we are working with them. The initial idea is that basically our role is more on the evaluating side, working with NCAR folks, and then UMBC, and then NOAA as well, related to how the bias correction. Now, basically the title not necessarily showing anything about bias correction, but we are actually pivot many times actually from the bias correction to basically just looking into the result, how the performance of the AQM model in terms of different regions. Now again, the figure here basically showing the EPA region 3. If you know how this part of effort is that we end up like separate so many different, not so many, quite a few regions, basically looking into the result. And basically, this is actually what we are doing right now. Again, at the December AGU, we would have a much more, actually, no, next month, we have the AQM workshop at NCWCP here, so we'll present that. Now, the last one here, again, this is actually working with the NSSL, is about machine learning, using machine learning approach to study the QPE for the West Coast region. So our part of effort is actually extended the machine learning approach currently developed or implemented already by NSSL using the MIMS data to study to improve the QPE. But the particular part is actually we are doing the sort of ensemble part of effort. It's more looking into, as you can see this figure here, we run different ensemble members. To the end, turns out the highlight in the red region basically shows like 35, something more beyond the 35 members. Yeah, 36 members basically. Shows some kind of promising result. So the paper is actually about done and was submitted to for publication purpose. But again, this is sort of like the next step is actually blending into this machine learning with MPAS model capacity, further looking into the AI events over the West Coast regions. So with that, I want to summarize with these slides in terms of just to show the joint effort, how we do. In this very dynamic environment, especially for those of you in DC area, you know that every day you heard is all about that, this, that. Anyway, so we are still doing the business as usual. We try our best to provide the support, to provide opportunity for students, and then work closely with NOAA line offices. That with that, I think we will be able to prepare ourselves better in the near future. Thank you.
Thanks so much, Sen. We have time for maybe one quick question in the room, if there is one. All right. So seeing no questions, Sen, we'll move on. If anyone has any additional, we might have some additional time at the end of the session, so we'll have you hang on if you're able to. But with that, we'll move on to our next speaker, who is Sarah Liu from the University at Albany. Feel free to come on up.
Well, it's not showing the slide yet, so, okay. No. Okay. Yeah, just give it a second, they'll let it go. Oh, okay. All right, so I just run the show. Okay. Go ahead, yes. Yeah. Hold 1 second. All right, well, thanks for the opportunity to present. So it's kind of follow on St. Charles there, the NCAS is a really collective effort from the center to conduct impact for NOAA research. But I'd like to share the experience from the individual PI, how individual PI from university can conduct the research that benefit to NOAA. So I'd like to really emphasize, I'm really sharing the research done in my group, because there's a lot of very impactful NOAA relevant research done by my colleague from DAES and ASRC from University of Albany, which is not present here. So I'd like to start from the lesson I learned from those my prior NOAA research before the UIFS community EPIC, before the EPIC era. So my very first NOAA project is actually to kind of try to improve aerosol cloud interaction in the NOAA's global model. So the approach we conduct actually adapt NASA GALA's aerosol cloud package. And then it's much more complicated, very detailed double moment, cloud microphase, and then a model, aerosol model. So, but you talk about 10 years later, NOAA right now is working on GoCard. It's a much simple the bulk mass model. So it's really, there's a big gap about what research community active working on and what the operational center is ready to take on. However, even we can't really know what's not ready to embrace the whole package. We actually at least work with EMC, and so the option to at least update the aerosol climatology in the NOAA radiation was implemented, and it's actually targeted for GFS version 17. And the improvement in the weather forecast was documented in the paper published by EMC. So this is one kind of, although the major project deliverable cannot translate into operation, but some element were being used. And then another project we work on is actually, again, we continue work with NASA GADA, and the project was like by CU. So we actually working on a JDAC-based aerosol data simulation system. And then So we adapt NASA's neural network retrieval, and then for VSLD, and then prototype LDDA based on gap aerosol, which is NOAA's operational aerosol model, and the JEDI DA system. So, and then right now at NOAA, the JEDI with the VSLD is actually under parallel testing. And then the project outcomes, well, this is not the only project held this effort, but collectively we know the JEDI-based aerosol DA system have been developed, and then we also have generated a prototype aerosol analysis for single year 2016, and then multiple year by another PI. So you can see those kind of efforts. The way we do is we close work with NOAA and then produce very NOAA relevant research outcome. But not all the research, although very interesting for scientists, but not everything can be translated to operation implementation. So we have another project, we really close work with EMC scientists, and we try to understand really how much complexity needed to really constrain aerosol impact in a weather forecast. So we actually couple a low resolution aerosol run with a high resolution GDAS run, and allow the radiation in the physics to affect by aerosol, and also allow the radiance calculation to consider aerosol impact. So we are talking about a more coupled system. But right now, up to now, the aerosol information from low resolution run is still not using by high resolution GDAS run. So this project outcome is really, we try to document our research outcome in a series of paper. So, really, the outcomes range from the peer-reviewed journal publication to some algorithm adapt in part of the GFS JEDI application. And then those lessons, I think is really, the one of the most critical element for productive R2O project is really a very close engagement with NASA's NOAA scientists, because you really have to know, what are the knowledge gap, and then what's really also operational constraint, all of this. So engagement with NOAA scientists, I think, is critical for a productive R2O project. And also we find knowledge sharing, is a very effective way to really advance the system, because you can see the previous internal aerosol modeling, aerosol DA, even the feedback, we largely leverage NASA GALA's research outcome. So then I'd like to share right now, within the UFS community modeling with EPIC support, and I'd like to talk about, how we are doing the research we're hoping to benefit NOAA, So this, I'm talking about two students they present this morning. So I will first talk about Anna's work. So this was funded by JTTI. So we have very specific goals, really try to compile flux measurement so we can really help NOAA to, when they do a parallel model development, they have additional data set to do process level understanding. So to figure out, what's the right way to tune the model. So this kind of project, I know this is a very busy slide, but she already presented her work. So basically the idea is really, we have 17 flux sites throughout the New York State. And then we try to see really, provide additional tool to quantify UFS scale with focus on land-atmosphere interaction. So this kind of project has very specific goal to benefit NOAA application. And another project also presented this morning by Michael, who is a Harvard student by Albany's NCAS consortium. So I had the pleasure to comment on Michael. So this project, we really, as I mentioned, we work very, very hard to advance the LDDA data simulation. However, the LDDA is really, ALD is totally under constraint system. You think about the model predict like 15 aerosol mixing ratio with dust CSO, different species. But ALD is just color integrate total ALD. So we really had no information on composition and no information on vertical structure. So Michael's project is really, is supported by KJ. It's really try to bring the capability based on JEDI to assimilate space LiDAR to really constrain the dust plume, smoke plume. So this project, the workflow is actually from EMC. And then, so we are really trying to, right now, Michael's work demonstrate current capability, but our ongoing efforts to bring the LiDAR profile. So the whole effort, again, you can see we build on existing the parallel system, so with very specific goal to benefit NOAA's operation. And these are, two projects demonstrate how how this kind of research not just only benefit NOAA, but also train next generation scientists for the enterprise. My next slide shows how the early career scientists can benefit the NOAA's application. So, so Dr. Shiwei at the back of the room. So we actually in the JDA we actually have capability to assimilate aerosol LD from various models and different trace gas. So the DA system already can have a forward operator to simulate those measurements at the observation space. So, and then what Shiwei did is really, he built a very generic, we take advantage of a very generic interface to interface JDA. So allow we to compare the model with observation with a very, I call it definition-aware comparison, because when we calculate model output, say model SNOX, we actually consider the kernel function, how the instrument, the information distribute with space, with vertically. So this is really, the goal is to provide a unified tool to evaluate models output in terms of trace gas or aerosol, but largely leverage JDA Advanced. So, and then this project was funded by JPS's Proving Ground and Risk Reduction. So allow this computer tool to allow us to take advantage of JPS's trace gas measurement, but also allow us to actually leverage whatever trace gas or aerosol DA capability building the JDA. So those three projects is funded by NOAA with very, very specific goal to help NOAA. But I'd like to present that some other research is not funded by NOAA, but still potentially can improve, can help NOAA's application. And his work is funded by NSF. We really try to understand how the dust affect AEW or how AEW affect dust, and with focus on radiation effect. And because African East waves is actually the major source of synoptic and mesoscale precipitation variability, and also is one of the most primary precursor for the tropical cyclone. So, so his work actually involved, in addition to analyze the mirror-to reanalysis, and his work also involved using the conduct experiment, using a CCPP single color model and UIFS. So, although we consider words try to understand radiation effect of dust on AEW, but we actually take advantage of a lot of tool, a lot of wonderful tool provided by UFS, just like CCPP, single color model. And then, so another research is actually supported by the New York State, the state agencies, really to understand air quality problem over New York City. And then we use a WRF-Chem, which is a widely used regional air quality model. So, and Leon's work is really, I don't expect you to see all the plots, but the take home is really, when we do different sensitivity and we do a text tracer to do source apportionment study, we realize the only way to improve New York City air quality is to actually reduce emission for the region. If you reduce locally in New York City, you actually get the ozone problem get worse. So his studies really show we need a regional solution to tackle air quality problem. So, and then NOAA have a lot of investment, field campaign, those kind of things, New York City, and then also NOAA was mandated by Congress to issue air quality. So understand for New York City, although it's small, although relatively small region compared to whole corners, but given its 20 million population, it's the largest mega city in New York. So understand how to address this is actually, we think can potentially help the air quality program for NWS. So anyway, for those ongoing project, for those NOAA project, we can potentially have, for a potential operation application, as I demonstrate for May Plus or for JDAC. And for the non-NOAA funded projects, at least we can enhance our understanding of those key processes for weather or for air quality forecast. So it's really still similar conclusion. I think the only way to have productive R2O activity is really close engagement with NOAA scientists. And then, we consider knowledge sharing is a very effective way. And then, but I think at this round, as we enter the epic era, so, my student, they was able to get a support when they run UFS, or they can use a single color model, do a lot of idealized experiment. So, I think the new thing is really leverage US community modeling resource, like, the repository, the support, API support. So that's, I think that's what I have. Thank you.
Thanks so much, Sarah. Any questions for Sarah? We have time for maybe one quick question if there is one. Maybe one I'll ask super quick is you highlight a lot of really great synergistic collaborations with NOAA scientists, and I think given sort of the focus of sort of this parallel session on students and new users, what advice do you have from your experience working with a lot of these scientists that are really effective in helping to build some of these collaborations, thinking about sort of potential new PIs in the room?
Yeah, I think I emphasize, the St. Charles talk about the center-wise effort. This is really individual PI. So, and then work with your faculty from university, talk about what you're interested in, and workshop like this is exactly perfect for this communication. A lot of ideas come to this kind of meeting and talk to people, let people know your work. And then also listen to what's going on, what's upcoming. And then from this, you can know what's the gap we can fill. And this is really applicable for the new PI and for students. Yeah. So it's really community engagement. Yeah.
Great. Thanks so much, Sarah. Appreciate it. All right, with that, we'll move on to our next speaker, who is Benjamin Cash from George Mason University.
Right, hopefully you can hear me. I always have trouble with these things. So I'm going to take a slightly different tack than the talks we've seen so far. I'm going to kind of drill down on a specific case study of work that we've done and how it then fed back onto the use of the model. So the title of the talk is that Project Resolution Dependence in the Seasonal Forecast System. Since we're talking about academic research that benefits NOAA, this is sort of the road to R2O. The idea is that our research will feed back into operations and hopefully improve it. And one of the things I want to emphasize is there are multiple ways in which that can happen. We often see the giant funnel where things go in at the top and have to hopefully make it down through a bunch of gates. That's not the only way in which you can engage with NOAA. All right, so a little bit of background about this project. The Seasonal Forecast System version 1 is currently under development. It's the UFS-based replacement for the extremely venerable CFS version 2, which is not quite older than some of the people in the room, but it is getting there. And the baseline development runs for that code are going to be made at C96 MX100, which is about 1 degree in the atmosphere and ocean. And the problem with this approach, one of them, is that this is much lower than the planned operational resolution because the planned operational resolution is expensive and you can only do so many runs at that resolution. The risk that this introduces, though, is that model behavior often changes unpredictably as you change the resolution. So it raises a question, are the baseline runs going to tell us what we think they're telling us about the model, or will there be some nasty surprises when we try to make this operational? One way to mitigate this risk that we discussed with the SFS development team is that you run a subset of the baseline experiments at the operational resolution and see what happens. And this is where our group came in, giving more eyes on the data and eyes on the model, and also leveraging our access to non-NOAA HPC resources to do some of these additional runs. This process was not without its issues. We did run into some potholes on this particular road to R2O, which is a good thing. So just taking the model and running it outside of its comfort zone benefits development automatically. You have new platforms and you have new configurations of the model, and you put those together and you have new problems. Some of the examples include that we ran into an unexpected limit on the number of files that the model was allowed to write in a single integration. We discovered this one by casualty when all of my runs died at the same point. That spawned a GitHub issue, so we got that one addressed. We also found out that the sea ice initial conditions, this is a slightly more substantial one, which worked fine when reduced to the 1 degree resolution, caused multiple crashes in the operational resolution. And this was eventually traced to some spurious sea ice volume and properties where the model was reporting sea ice properties in places that it wasn't reporting that there was any ice, or it was reporting ice over land. And it was just a problem introduced when those initial conditions were generated. Getting past this eventually required us to hack SICE to turn off one of the checks. This is not a great solution to this problem. I would not recommend this one going forward, but we were stuck and really did need to get unstuck from it. Really, it needs new ice initial conditions to resolve this properly. And again, this spawned a long discussion with the MC developers and a GitHub issue. And the point I want to make is like, none of these are exactly eureka moments. Like, I am not going to get a Nature paper out of the file limit that we encountered, but it still provided actual tangible information to the model developers that they could then act on and in at least a small way improve the model, just as a result of, again, taking it outside of its comfort zone and making it do something new on a new platform. All right, so that's fine, but what about the science question that our group set out to investigate? So looking at what happens when you go to a higher resolution, so C192 versus C96. What I'm showing up here is a postage stamp of plots. The one up in the corner is November. These are 10-year runs, ensemble means. November, December, January, February. Difference in temperature from the new runs to the old runs. And the main takeaway from this is that they are bright red and they get redder as you go along. So there's a big increase in temperature in the C192 runs we did compared to the baseline. This would be fabulous if the C96 runs had been too cold and we were warming it up, but that is not what happened. C96 was already too warm. So this is a pretty significant degradation relative to the baseline, which naturally spawned the question, what in the world happened here? So we decided to dig into this a little bit further. We looked at some of the usual suspects for when your temperatures go strange, like looking at total cloud cover. It's the same layout, and again, don't focus too much on any of the details of any particular plot, but now my plots are mostly blue, indicating that we lost a bunch of clouds going to the higher resolution, which presumably is going to give us more shortwave at the surface and would plausibly explain why my temperatures jumped up like that. So it did hold together, and it suggested, and we haven't gotten to the bottom of this yet, but it suggests that maybe there's an unforeseen sensitivity in one of the cloud parameterizations to resolution to see such a big jump in behavior when we made this change. Okay, so I said it might be due to shortwave resolution or shortwave at the surface, so we looked into that. Again, same postage stamps. Again, the one up in November is mostly red. Indeed, we're getting more energy to the surface. And then it gradually sort of planes out over the course of the simulation. But it is consistent with the increase in temperatures and the decrease in cloudiness. Right, since we are seeing this big change in temperature across the whole globe, one of the things that this brought to mind was, well, are we seeing a change at the top of the atmosphere? Radiation balance also. Are we just getting more energy into the system, or are we reflecting less out? So we decided to take a look at that, and this is where we ran into something that really was not anything we were expecting. So I'm showing here, this is now just from C192, so my runs. This is the top of the atmosphere, downward shortwave. This is just, the plot here is just the zonally asymmetric component. So I subtracted off the zonal mean, and I initially did this just as a post-processing sanity check, because I was the one making the monthly mean out of this, and I wanted to make sure that I was getting something that looked rational, and instead I got this pattern, which should be near zero, but instead we're getting magnitudes more like 1 watt per meter squared, which is not enormous, but it's not nothing either. And at first I thought I have indeed screwed up my post-processing and I have some weird imprint of where the sun is, except these are all supposed to be from daily mean files. So there shouldn't be any information about where the sun is left in what I calculated this from. All right, so this is genuinely weird at this point. And usually when I run into something that is genuinely weird, my first thought is, this is user error. I have done something strange in either the calculation or in setting up my model run. All right, so let's look at some other model runs and see whether or not it shows up there. So we went back to the baseline calculations. This is the same set of postage stamps. So these are not runs that I did, so that I cannot be held responsible for any errors that were made in them. And we see very similar magnitudes to what we're seeing in the runs that I did. There's some interesting dependency on the month in terms of the magnitude in the pattern. It sort of progresses across the globe. December, the magnitude is much less than it is in February. I have no real explanation for why that should be true. And I'm not going to show a whole bunch of patterns that look like this, but we looked at all of the various flavors of the model that we could find and had data for. It goes back at least to the prototype P8 runs. Phil, who's on the other side of the air wall, I think at this point, looked at it in some of the runs he found it also. So now it can no longer be blamed just on my poor Python skills. It really is there. So it is some kind of persistent, previously unidentified issue in the model. Current thinking is it's likely related to the calculation of the diagnostics. That's probably not actually in what the model is seeing, but in what the model is outputting. And then again, one final sanity check just to convince you that this really is kind of odd. I grabbed some data from a random CMIP6 model. I think this one turned out to be NASA GISS, and calculated this same thing. And if you look and can read from the back of the room what those magnitudes are, they're 0.02. So about 40 times less than what we're seeing in SFS. And the pattern is completely different. So the explanation for this is still unknown. We're still trying to figure out what happened here. One of the points I wanted to make with this, though, in terms of the research to operations pipeline, is this is not something we were looking at whatsoever. We certainly did not set out with a research task of, I wonder if there's something really weird in the zonally asymmetric top of the atmosphere shortwave. No. It really did just come out of having more eyes on the data and deciding to make this one particularly odd calculation just to make sure that I hadn't done something dumb, and then something interesting came out of it. So summing up in terms of this particular study, how academic research can benefit NOAA, I mean, obviously the first one at the top, developing and incorporating new science. We didn't particularly do that here, but that is sort of the classic R2O mode. But there's a lot more to R2O, I would say, than that. Earth system models and their outputs are incredibly complex. Errors can be subtle. They don't always reveal themselves in standard diagnostics, as happened in this case. Even when the model errors are obvious, the cause may not be, so it takes a lot of work to dig them out. And this is a place where putting data and models in front of the academic researchers can help identify and resolve these model issues. And I submit this is also a form of research to operations. It does not need to go all the way through the funnel. It can go through your collaborations with your partners at EMC, where you go, I'm looking at this and this is really weird. Have you seen this before? So I could stop there. I haven't gotten any notes from the back of the room yet about my time, so I do want to have one more thing that I wanted to go into here, specifically because we're in the new user and student track. The topic at the top is how academic research benefits NOAA. I feel like it's also important to go into how we're working with NOAA models and data benefit the people in the room who are thinking about becoming new users of this modeling suite. What is in it for you? Why am I bothering to do this? Why do I think it's worthwhile? And so I threw up a list of ideas here. One of them is funding. Let's not sugarcoat this. Funding is great. We all like having funding. And NOAA funding typically focuses on improving NOAA models. So this, because the community is still growing, I can put that in a particular way, this can be less crowded than some other opportunities that are out there. It is worth looking into this as a place to identify funding, or at least it's just a different pool to draw from. I would also say there's an element of public service and an element of self-service. These are the models that are safeguarding lives and property right here, right now, where we are all sitting, and it's an opportunity to improve them. Literally everybody sitting in this space has an incentive to make these models as accurate as possible. And finally, because we are research scientists and science is great, NOAA research models cover a massive range of timescales and phenomenon. there's very likely an application that covers your particular area of interest that you could work with as a tool for you doing your science. It is important, minor caveat, to be mindful of the developmental stage of the code you're in. You may discover a bug that nobody's going to take the time to fix because we've gone 3 versions past that and the bug didn't show up again. And we're all going to hope that it just stays gone. And also finally, the model data is increasingly available if you don't want to go through the effort of installing and running the model yourself somewhere. The analysis that I showed about the weirdness at the top of the atmosphere shortwave could have been done without me running any integrations myself. My integrations happen to point me towards it, but it could have come purely out of the analysis of the data that's already out there. So I'll just leave you with the thought that I definitely see that increased collaboration benefits both NOAA and academia. It is far from a one-way street. And I appreciate your time. That's all I have.
All right, thanks, Benjamin. Time for one question. There is one.
Since this is like an audience that's full of students, I'm going to echo that moral of the story you have there, which is that you could have discovered it without touching the code through, but research is a long and windy process. You don't know what kind of stuff you're going to find out, so I think that's perfectly fine. And I think it's going to be something that the students here, as they get to doing more research, are going to discover that you thought you were going to do this thing, but poof, your paper is on some other thing.
Yeah.
That's perfectly fine, and it's very normal.
Yes, yeah. 100%. If you poke at it, you will probably find something. Most of the time what you find is a mistake that you personally have made. But sometimes you find something that you can't prove where you have screwed it up, and then you have something interesting.
Thanks so much, Benjamin. All right, and with that, we'll bring up our last speaker, which is Joseph Chan from Ohio State University.
Do I need to, Yay, I don't have to wave a magic wand or anything. Lovely. Alrighty, so hello everyone. I am Joseph Chan. I am an assistant professor at the Ohio State University Department of Geography. I started working there in January of 2023. And so it's really a big honor for me to be here this early in my academic career as a scientist. And so, as Daryl Kleiss has happily outed me, I'm a DA expert. And so I'm going to talk about data assimilation. I'm going to talk about how we can potentially benefit NOAA by improving the exploitation of observations in data assimilation. And in case it was not clear, the motivation for this sort of research is that data assimilation is an important part of NOAA's NWP, Earth System Forecasting apparatus. Fundamentally, we are all about combining observations with a pile of model runs, and we use that to figure out what the best initial conditions are under some statistical assumptions, and then we launch our NWP for society from that point. And so thus far, there are a couple of things that I thought would be pretty interesting for NOAA and will benefit NOAA's advancements in NWP. And so I'm going to present a series of vignettes, so to speak. The first one is basically, if I want to be completely honest, the first title is, What Can Possibly Go Wrong with Data Assimilation? And this was actually not user error. This was an actual science thing. The second one is from outer space. We're going to talk about how we can potentially use things that astrophysicists are doing anyway and see if we can use that to improve data assimilation and therefore NWP. And finally, I'm going to present a bit about a potential, sounds like AI but not quite AI approach to increase the number of ensemble members we are working with in NWP. And so let's start about what can possibly go wrong. And so some background. So I did my PhD on assimilating infrared radiance observations. So as most of you probably know, that We get a ton of these observations from geostationary satellites on a very regular basis. I think we get like a pixel every 10 kilometers every 10 minutes. That's a lot of data. And so there has been a lot of research into using these observations to improve convective scale data assimilation and convective scale forecasting. And a really common finding is that a particular class of data assimilation methods seems to work with these observations. And so this class is known as the ensemble Kalman filter. And this is very important because one of the assumptions we make in ensemble Kalman filters is that all of statistics are normal. As it turns out, they are definitely not when it comes to the infrared. So what you're seeing here it's kind of abstract. The diagram you're looking at is kind of me calculating the skewness of the distribution at every grid point in an experiment. And I realized that the skewness is mostly negative. A normal distribution is very pretty. It is a bell curve, it's beautifully symmetric. Any kind of skewness means that our distributions are not Gaussian or not normal, and we should anticipate problems happening. And the other one is that infrared observations are generally very strongly affected by convection, which has some fairly nasty non-normal properties as well. And so these seem like theoretical problems, but they have very real impacts. And so that really, I have two questions that I have looked into, which is what kind of practical problems can happen because of this violation? And can we mitigate these issues while sticking to this kind of simple, kind of fun ENKF algorithm? And so I did some virtual reality experiments. And so what you're seeing here is a nature run. This is like a virtual reality simulation that I define, and I then generate observations from that virtual reality and try to assimilate those observations to see what can possibly go wrong. And so this is the first one of the indicators that things have indeed gone terribly wrong. And so what you're seeing in the first diagram on the top is humidity of, there we go. Yes, humidity of clouds before doing any kind of data assimilation. And as you know, in just high school physics, maybe thermodynamics in college, when we have a cloud, the saturation ratio should be kind of close to 100%. So relative humidity should be close to 100%, if not exceeding it. When I looked at the clouds created by data assimilation, I am getting clouds with, like, what is this, 80% relative humidity? That is spectacularly wrong. And so, as you know, when we have like air that's fairly dry and we have a cloud in it, it's going to evaporate, and basic high school physics will tell you that we are going to cool the atmosphere, and that is indeed what happened. We saw the manifestation of a very strong cold bias across most of the troposphere. Blue here means cold bias, and as a result, I have some fairly spectacular results. So what you're seeing here is are measures of error in my experiments. Green is good. Green means that using infrared observations did some improvement. Purple means things have gone wrong somewhere. It's like purple means doing something is better than doing nothing is better than doing something. That's like the worst possible scenario you can ever show a DA person. And just to defend my community a little bit, most of the time we work on data assimilation for 24 hours or so. And indeed, for the first 24 hours, things are green. We're getting some fairly decent results, but afterwards, things kind of go haywire. And the reason for this is just, again, because we had clouds that were just simply too dry in the humidity sense. And so just to confirm that, I just disabled like the updates to the cloud fields, and our results are green and happy. So in other words, what I've done in this study is that I have traced a particular theoretical problem, which is an assumption violation in the statistics that we use for data assimilation, and I traced it down and showed that, hey, there is a very real impact here, and we should really think about this when we design data assimilation systems to leverage these infrared radiance observations. And so that's the first little vignette. There is another big finding which I thought was very good, was that apparently there are some fairly interesting interactions between the way we determine an observation is good or not and the non-normal statistics, but that's a whole story for another time. And so that's my first little vignette that I wanted to present on that I think will benefit NOAA. Hopefully NOAA will look at this and realize, hey, we need to be careful when we are assimilating these observations. And now to outer space. And so I have been working with a postdoctoral fellow from the Department of Astronomy, Will Lazak, and we've currently looking into assimilating a cosmic radiation measurement to improve NWP. And so what we're specifically looking at is muon fluxes. And so in case you don't know what cosmic rays are, actually no one quite knows what they are. Cosmic rays come from outer space, from potentially unknown sources. But the important part is that they are very high energy particles. And so when they hit the atmosphere, all kinds of magical things happen. It sets off a shower of like subatomic particles. The one that I want you to pay your attention to is the mu symbol. That is, those are referring to muons. Muons are kind of like electrons, but a lot heavier. And as it turns out, when muons travel through the atmosphere, if they hit an atmospheric molecule, they kind of just fall out of the way. You don't measure them on the ground. What that implies is that the amount of muons we see at the surface of the Earth depends on the density of the atmosphere, because the denser you are, the more molecules you have to get in the way of the muons. And so there is a response whenever we have varying densities in the atmosphere, and there you see a response in the number of muons we catch on Earth. And this is an observation of opportunity because astrophysicists are doing this anyway. This is almost at no cost to us. We just have to figure out ways to grab the data from them and then leverage that in data assimilation. And I learned, apparently, that muon detectors are fairly cheap to make and are oftentimes assembled in college astronomy lab courses. So this is a potentially rich source of data that we can use. And so our hypothesis going in is that maybe we can use this in data assimilation. If we are successful, perhaps NOAA can give a shot at this and see if they can use it as well. And so to kind of pathfind our way through this, we did a series of day-long experiments with Tropical Cyclone Freddy. We just picked this case because it was very tragic and very dramatic at the same time. Killed about 1,400 people and cost about $1.5 billion of damages in Madagascar as well as the eastern part of Africa. And so I'm just doing this with WRF and a fairly simple data assimilation setup. And what shows up, which made us really happy, was the fact that assimilating the muons does seem to be improving the performance of data assimilation. And depending on how big your sensor is, it can outperform like assimilating a surface pressure measurement. So there is something going on inside the muon observations that is kind of unique to muons and is not quite there for surface pressure measurements. And we think it has to do with the integral nature of muon observations. Yeah, and so bigger sensor is better, and the sensor sizes we want are apparently fairly practical according to astrophysicists. And in fact, I think the biggest sensors they have in the field are a lot bigger than these guys. And so this is an observational opportunity we can consider like moving forward to help improve NOAA's NWP system. And so that's the second one. And for my final like little vignette today at this session, I'm going to talk about a potential way to increase ensemble sizes. And this is work that is funded by the Office of Naval Research through the Young Investigator Program. And so I have to take a step back and explain what the problem is. In data assimilation, especially ensemble data assimilation, we need to run a whole ensemble of model runs. That is computationally expensive, but if we run too few of them, the statistics we need are not like of high enough quality. That's why we have to run as many of them as we can. And so the goal of this project really is to try and find ways to create additional ensemble members without needing to run additional like model runs. And this is stuff I'm collaborating with Liz Satterfield, Julie Rubin, and Ed Heyer from NRL. And so like the idea here is very simple. So if this is the data assimilation workflow, we have to run a short forecast. We then simulate the observation and then integrate that observation into our ensemble. And what I'm proposing to do here is to add 2 additional steps. The first one, I create virtual members that I then feed into my DA system and then hopefully have that improve DA. And then after we're done with data assimilation, we remove the virtual members so that we don't have to integrate them forward. And so we have some preliminary-ish results here. So the good news is that the virtual members are fairly realistic. So what you're seeing here is the horizontal flow patterns and geopotential heights at about 250 hectopascals. And honestly, if I didn't have the labels there, I can't tell which is real, which is the virtual members. So that's quite nice. And currently, PSGC, the method is called probit space ensemble size expansion for Gaussian copulus. I just call it PSGC. And it's fairly cheap at the moment. I think it cost me like 10 cents to generate 100 virtual members, but then I get discounts at Ohio State, so that might be part of the reason. And so another interesting thing about it is that I can imbue user information into the system. So one thing that we know as data assimilation people is how correlations should look like. And so on the left is correlations without correction, and on the right we have correlations with some corrections that we can do as DA people. And so that's particularly interesting for those of you who have heard of ensemble modulation, but that's a story for another time. And so that's it. That's all the little vignettes that I wanted to share. And again, the ultimate goal here is to benefit NOAA's forecast systems through improving the data assimilation system. And that's it. And that's it for me. Thank you very much for your time, and I'm happy to take questions.
One question. I know we're right up at the start of thinking about the break. Yeah, go ahead.
Could you go back to the second presentation with the muon fluxes, the specific graph of the test case? Yeah. So I noticed that NoDA performs significantly better than integrating surface pressure. That seems like a pretty interesting finding. Could you talk about that?
Yeah, sure. So that's a great observation. You're referring to the first 5 hours of this experiment. So what is going on here is that I think is a side effect of non-normal statistics. So what's going on is that the surface pressure measurement we are simulating was starting to pick up on Tropical Cyclone Freddy, but none of our ensemble members were quite there yet. And so when the experiment is simulated the surface pressure measurement, it kind of went wonky because the statistics were just not there yet. And you notice it stayed persistently above no DA for a while. That's just simply because my experiment started to reject the surface pressure observations. But after a while, the data assimilation, the ensemble started to agree with the observations a bit more, and so then the performance flipped afterwards. Hope that answers your question.
Yeah, that does. Thank you.
You're welcome. Great question.
Awesome. So let's give Joseph and all of our speakers another round of applause for sharing all of your research with us. I think.
And let's also give a round of applause for our chair for putting the session together. And as we said, I think we're right at break. We'll be back here at 3 o'clock. I think this is probably the sessions coming up everyone's looking forward to, getting your start in NOAA and also networking. So for you new students, I highly encourage you to come back, bring more of your friends, and we will see you guys at 3. scheduled for the rest of the afternoon between now and 4:30. Our first panel here, I'll introduce our chair, Mike Eck, in a moment, is a panel on starting your career in NOAA. We'll run that for about 45 minutes. And then after that, another panel, Mr. Eck will be running as well, chairing, and that'll be effective ways to network. Then we'll do some closing announcements. I will share, stay. I am supposedly, according to the instructions, Allison's will give me a jar to draw a raffle ticket. So, you know, stay around to the end. Also, this is going to be the best session anyway. This is going to be really effective for you trying to get your career started, so I hope you all stay. Again, please ask questions. Folks online, Slido, please reach out. I don't think we've had many Slido or online questions today, so please interact. We want to hear from everybody. And I think with that for announcements, Mike, are you in the room? I don't see you. Okay, well then I'm going to hum a few bars for a minute then. Yes, let me make sure you go find Mike if you don't mind, ladies. Don't you just love live events, folks? Just don't ask me to ask any, do any jokes. Meteorologists, I'm not that funny. Here he comes.
Hey, there's Mike.
Mike, you're gonna get a demerit. Yeah. You're also my chair.
It was not only that you were the last one, Mike. You were explaining to people everybody out of the room.
All right, it gives me great honor to introduce our chair for our two panels today, Mr. Mike Eck.
Thank you very much, sir. Okay. Oh, you don't have to clap. So these are a couple of sessions focused on, helping our early career, mid-career, well, other scientists as well. But it's just a time to talk. The first one is about starting our careers at NOAA. So we have myself, thank you for your patience, Logan Poole, Tracy, how do you say your last name? Fonara, okay. Allison Gregory, and Jen Poole. So I guess what we can do is just start walking through the slides we generated. And so I'll let, you're first. Okay. Oh, sorry. Why don't you just run up real quick? I'd like you to come up here so you can see your slide.
It's just my mug, so it's fine. I just got these professionally done like a couple weeks ago. The headshots. Oh, it looks great.
Oh, we have 3 minutes.
Oh gosh. All right. For you, those who don't know me, either through all the incessant emails I've sent about this workshop, I am the EPIC Deputy Program Manager and a physical scientist for NOAA. So EPIC, the Earth Prediction Innovation Center, I know it's probably been thrown around a lot this week, is within the Weather Program Office. And I joined, I guess you can read my background, but I've been at EPIC for the past 3+ years. But I've actually jumped in and out of the contracting world to the Fed space a couple of times. And I was recently promoted to the Deputy Program Manager role this past year. So, yay. Just more responsibility, that's about it. So I was a Weather Service meteorologist in Jackson, Kentucky, and Albany, and then jumped out of that Weather Service space to be a contractor in EPIC, and I got back on the federal government side. I went to school in Millersville, University in Pennsylvania, and University of Wyoming for my master's degree. I know I jumped all through that slide, but that's just an introduction for myself.
Okay. So let's go to Logan. He should be online, that's right.
Yeah, maybe people can hear me. That'd be great. Literally just got in just a moment ago, so apologies if that's taking a bit of time. My name is Logan. I am a meteorologist at the Weather Forecast Office in Jackson, Mississippi. Yeah. 1 second, apologize. Had a little echo in my ear. So my history, I began as a private sector storm warning meteorologist. So did a lot of warnings and that sort of thing as an operational Met. After that, I did some web development. I've done some national broadcast television, stands up in front of storms, things like that. And currently, since 2020, I've been a FO forecaster here at the Weather Service office in Jackson, and got involved last year with the UIFCW25, and really excited to participate this year and see if I can be of any service to folks.
Did he finish? Oh, apologies. Yeah, Logan, you have 3 minutes, so I just wondered if you wanted to do anything more in a nutshell, your feeling about what you've been doing, and your continued role, I guess you could say, in NOAA?
Sure, yeah. I wasn't sure what the timeliness. This is, again, someone said before, live TV, if you will, right? So really my primary role at the current time is I am a forecaster. So I do all the base level things that you might see coming out of the Weather Service office, whether that be warnings or forecasts, general connecting with the public. We're sort of the frontline users, if you will, of the systems that hopefully some of you will go on to participate and design and create and make better. And and we'll talk about this a little bit as you go along, but there's definitely a top to bottom sort of way for you to be involved in NOAA and in the system as a whole, whether that is someone who is helping to develop these very high level pieces of numerical weather prediction models, or whether you are maybe someone who's more interested in the AI machine learning side of things and you're helping develop some of the tools. But also there's opportunities if you are someone like myself who has some experience with that, doing some IT and development, but also someone who likes to be more on the application side. So there's a huge plethora of things that you can do, and all sorts of backgrounds and opportunities and tools for you to make that happen for you. My experience and career is wide, extends a wide breadth of experiences, all the way from private sector to television and broadcast to the IT sector, as well as being an operational forecaster. So if any of those things appeal to you, then there is room for you to sort of make your mark and get involved. So I'm hoping we can talk a little bit more about that as time goes along. And if anybody has any questions for me as we go the next little while, then I'd be happy to address that too.
Okay, fantastic, Logan. An eclectic, broad background. Will everybody have access to our emails? I mean, if they want to follow on with, okay, fantastic. I think that's how it goes. Okay, let's go to Allison.
What did I say? Okay, hi everyone, I'm Allison. You guys were in the student session, so you missed my talk this morning, but I had a talk about a social science survey I did for the UFS community. So that's currently what I do. I kind of help all of the people who are working on this modeling platform collaborate with one another better and understand one another better. And I have been here for 2-ish years now. So I have kind of an interesting background. I got my bachelor's and then master's degree in political science and environmental sociology, and then a master's in environmental sociology. So that was kind of like my first go at doing a career. And then I worked in the nonprofit public space doing energy policy for a few years, and that was good, but it was a little grinding on the motivation, you could say, in terms of what you can, legislation-wise, what you're able to pass and what you're not able to pass. So I'm happy to talk about that part of my life as well, if that's interesting to folks. But then I decided that I kind of had a lot more brain to offer than I was currently using. So I went back to school for atmospheric and oceanic science. And so I'd love to talk too about the non-traditional paths of if you want to go back to school, that's totally an option. Don't commit to something and be like, well, I already did this and I'm too young to do, you can just go back and learn again, start over, whatever. It was a vision board process. I could tell you all about it. But so yeah, so you're never too young to switch your career. I'd be happy to talk about that. I also did the Early Career Leadership Academy. It's a program through AMS every summer, and that was last summer. And that was a great opportunity to kind of see what opportunities are available in terms of collaborating with AMS in terms of my current work and kind of other ways you can involve with AMS going forward. Also, I work at UCAR, which is the University Corporation for Atmospheric Research, and it's affiliated with NCAR. But UCAR is, if no one's ever told you, UCAR is more of the school side of things. So it's kind of like how we do like the scientific partnerships and collaborations. And we partner with maybe like 80 universities. And so that's kind of how I work with NOAA as well, is I'm able to wear a NOAA contractor hat, but also work at UCAR, so I don't have to be a federal employee, which there are pros and cons to that, of course, and I could talk about that as well. But yeah, and also I am a new mom, and like I said, I'm a non-traditional, you know, I went back to school late in life, so I'm happy to talk about any kind of like personal navigation of your careers as well. Good.
What was that? There you go. So let's move on. Oh, to me. Do we want to do me at the end or something, or? No. Okay. Well, I have a similar slide in the networking. Currently, I'm the director of the Joint Numerical Testbed Program, at least for a couple more weeks. I'm going to retire in November. But I'm going to come back as a casual so I can actually do some science, so that'll be fun. It's part of the Research Applications Lab in the National Center for Atmospheric Research. I did my BS and MS in atmospheric sciences in the early 80s, you can kind of go, whoa, at Oregon State University. And then my career evolved and family and everything like that. I was later in life, too. I went back for my PhD. I did it working at Wageningen University in the Netherlands. Yes, my fellow Dutchman is although he was at Delft and I was at Wageningen. So that's my academic background. And I started out working in the Anchorage forecast office up in Alaska. Technically, I worked for the state, but I was in the Anchorage forecast office, and I previously had worked as a summer intern on satellite meteorology, and that was very informative on the beginnings of what does NOAA do. The state job later that I did, again, in the forecast office in Anchorage, was mountain meteorology and avalanche meteorology in the winter. So I did a lot of field work, forecasting, etc., public service announcements and whatnot, and then fire weather in the summer. So I went from fire to ice and then kind of toggled back and forth between those. Went down to the lower 48 and I worked in the Seattle forecast office. And actually I moonlighted as a private sector meteorologist for Northwest WeatherNet. I did that at the same time, and it was very exciting, kind of to go into that non-traditional area. I was a research assistant when I was at Oregon State. I've been a research meteorologist connected to Wageningen University for a number of years. And actually part of my evolving career, I did a 2-year stint at KNMI, which is the Royal Netherlands Meteorological Institute. So think of it as the NWS in the Netherlands. In fact, I knew an awful lot about the land model and the boundary layer model that was developed at Oregon State that we shared then with NOAA and others, and NCAR. But when I got to NOAA and NCEP and the Environmental Modeling Center, where I was there for almost 20 years, I was deputy and for part of the time an EMC land team lead. But it was interesting, when I showed up, I really knew a lot more about the European Center model than I did about the NOAA models, and so that raised some eyebrows, but I quickly learned. I've been the JNT, Joint Numerical Testbed Director, since 2018. I had an opportunity to move to Colorado. My wife was from Colorado, so we thought it was a good change. I've been involved in a number of WMO activities, World Meteorological Organization, World Climate Research Program, and a GWEX program underneath that, the Working Group for Numerical Experimentation. All the operational centers in the world work there, so I've been doing that for a number of years. I've been involved in AMS, and all of that was quite interesting. Over the years, I was worked on the Hydro Committee, where I was chair also of the Forecast Improvement Group. But what I really like to do is show this R2O funnel. This was created by Louis Uccellini, former NWS director, and it just shows the various pieces of the research to operations and operations to research. And I did kind of an assessment a couple years ago. I decided, oh, well, wait a minute. When I was at Oregon State in Wageningen, I was way up high in this funnel of the research. When I was a forecaster and private service meteorologist, I was in Alaska and Seattle. And then at KNMI and then at NCEP, I was kind of in that near operation side. And now at NCAR, I'm in the testbed realm. So I guess I can say I've kind of covered all the funnel. So maybe I'll stop here. Again, we'll have emails, but we'll probably go on to Tracy.
Hi, everyone. My name is Tracy Fanara. So, you know, there are certain people in the world that are always chasing. They're always moving the goalposts, changing the game, changing the goals, changing the rules, but always chasing. Anybody else like that in here? Raise your hand. Yeah. Yeah. Well, the rest of you, Guardians, will love to get you in operations. But I have always been an innovator, and I'm always moving the goalpost. So my career has been throughout the academic, private, nonprofit, and government sectors. And all the time, like I find a problem, I pivot, even if it changes my scientific discipline, even if it changes my skill sets that I need. So I started off at the University of Florida. I realized that deforestation was a huge problem. So I went and worked in land development. I thought being on that side would really, you know, I could change things. I realized that I couldn't, and I also realized real quick that stormwater was a problem. Our stormwater regulations were not adequate to prevent algae blooms, flash floods, things like that. So I went back to school to prove that there was a better way. So I guess I went back to school later in life. But I really focused on low impact development. So retrofitting urban areas to mimic pre-development subsurface hydrologic conditions. I know that that sounds really technical, but it's just making it seem water-wise like no development was there. So when I finished that, I realized that I really needed autonomy. Autonomy was something that was really important to me. So I was offered a position to lead a research program at Mo Marine Laboratory. And even though it was the lowest paying job that I had been offered, I took it. And it was awesome. I loved that job. I made peanuts, like really peanuts, but I loved that job. I was developing technology, honing my communication skills, and telling people, researching Florida red tide, a toxic algae species endemic to the Gulf of Mexico. 2018, we had a pretty severe bloom. Toxic aerosols were reaching 30 miles inland, causing respiratory irritation. People were getting sick. Wildlife was dying in the tons on shorelines. Businesses were going down. We lost $2.7 billion. And people were pissed. We didn't have the answers. And the reason was because biologists were taking samples near the shoreline and trying to understand a microscopic species in a huge body of water that acts differently in the natural environment than it does in a laboratory, when really these blooms were influenced by hurricanes, Saharan dust, ocean currents, wind events, rainfall, nutrient loading. So I realized that we needed to answer these questions from a much bigger picture. So when I was contacted to work for NOAA as a coastal and ocean modeling portfolio manager, I jumped on it. I really wanted to create a future where coastal and ocean models were part of the Earth systems modeling efforts at NOAA, and that's exactly what I did. And then in March, the opportunity, I would say, to leave NOAA with the deferred resignation came up. And I left because I was at NOAA and I saw all of the gaps in our hydrology. I saw there was a lot of flooding events not being captured. I saw that there was a distinct discrepancy between between the communications. You know, we had weather being in charge of comms when, you know, meteorologists are not hydrologists. And so I left to create a hydrologic platform. And that's exactly what I'm doing now. Project Inky is a hydrologic platform in partnership with the Alabama Water Institute and the National Water Center. And hopefully we're going to make consumable products. And you know, I was doing this before the Texas event occurred. And that was awful. And honestly, I was going to give up on it. I was actually going to pivot again on July 3rd. And it was just like everything kind of like came together. And so that's what I'm doing now. Also, my little cousin, when she was 11, she said she wanted to be like Kim Kardashian. So I started doing TV shows, and I do a lot of TV shows.
Thank you very much, Tracy. You got a lot of passion, and that's wonderful. And a lot of pivoting, and that's wonderful as well. So potential questions that we put together. Think about these things, and then we can entertain some other comments and thoughts. How did you first learn about NOAA? Well, maybe we should ask our panelists first. Oh, you're right, in terms of the time, sure. Sure. What was your first job at NOAA? We've talked about those things. Is there traditional career paths? Well, we can see that we've kind of been eclectic about that into the NWS and NOAA Lab, NOAA headquarters, et cetera. And what are some of the non-traditional pathways in NOAA through another agency, academia, private sector, industry? And you can see from our panel here, and our, thank you, Logan, as well, that we've kind of explored different aspects of, well, I'll just use my funnel research to operations, but there's many things you can do along the way. And I think the one takeaway is, and you alluded to this, Tracy, is doggone, the whole world's connected. The whole ecosystem, the whole environment is. And so you can't just look at the meteorology and just look at the hydrology or just look at the ocean. You have to consider everything in a fully coupled sense. If you don't, you're going to miss some things. And that's what we need to explore. And that's why the UFS is a more holistic model. So, questions from the audience?
We have a lot of time.
We do. We have 25 minutes, right?
If we want to sit here and stare at each other, that's fine too, but we'd rather have your questions.
As one of our other speakers said, we're all a little, introverted. This is a place to get out of our introvertedness and, share. No one's going to judge you.
Yeah, Ben.
Yeah.
Ben's going to break the ice.
Yes, a question.
Thank you, Ben.
Thank you all for telling us about yourself a little bit. The elephant in the room is what's going on at NOAA. So all of us up here have NOAA experience. Some have left, some are leaving. But to the students, what can you tell them, if anything, moving forward, despite the, let's just call them uncertain waters of NOAA? Any advice? Because that, I'm imagining they have some uncertainty that might be nice to address.
Shall we start and just let the...
Okay.
And then we'll pull you in, Logan.
Well, I was just going to preface with Tracy and I are probably allowed to say a lot more than people who are already knowing. But I don't know. The only thing I would want to highlight is the like creative ways that you can be involved with NOAA. I applied for this job through the UCAR page portal, and it just happened to say NOAA contractor. And I think a lot of other places like CSU up in Fort Collins has a climate center, and they also hire NOAA contractors through there. So I would just say, looking around at your cooperative institutes, you can find ways where they are receiving NOAA funds, but you're not exactly in the pool of uncertainty that NOAA has. I mean, and of course, like uncertainty was introduced in my work as well, but it was just a lot less dramatic, I think. And I'll leave it at there for now because I don't have as much.
I mean, we're not the EPA, right? And I say that because I really feel like the EPA is one of our most important government agencies, but I think that NOAA is more protected than other agencies. And it's because lives and property, economy, navigation, defense. There are so many different aspects that we cannot drop the ball that NOAA is responsible for. So I think that, you know, the first step is hiring back all those people that, you know, how many are we hiring back now? Like 200? 450. 450 at the weather. That's a little bias.
That's the only exemption that they have.
Okay, I'm just kidding.
We have 450 job openings, and 2 weeks ago, 3 weeks ago, we were allowed to hire them, and we were allowed to start doing a lot of the direct hire procedure.
Yeah, so lots of jobs open right now. For a new scientist, I always like to look at in the darkness, to look at the light. And as a new scientist, there's 450 jobs open, you know? So taking advantage of that, I would say do that. I left because of, yeah, there was some uncertainty. But I also, as I said before, I really need autonomy. And in my position that I had, I didn't have much. I tried, which was the problem. But yeah, I mean, things seemed a lot darker than they seem now from my perspective. But Jen can speak more. She's still there.
I am still there. A couple things. One, if you're interested in NOAA, please apply. There are so many passionate people who work at NOAA who care about the mission, who care about their position they're in. And we love to see young, bright talent come into the agency. Rowan is an example from interning this past summer. If we could hire her right off the street, we would. So that's number one. I'm getting emotional talking about it. Two, I did start my career as a government contractor. So if you keep an eye on different private companies, there's no good central location for these jobs. AMS board lists some, but private contracting companies will have contracts within the federal agency. So I started as a contractor for NESDIS, got that experience, and then I was able to get into the National Weather Service as a Fed. So that's also a way in to get your foot in the door. You want to kick it over to Logan? Yeah. Logan, do you have any?
I have a couple of things I can say. First of all, I'm about as far away from management administrative decisions as you can get, which I kind of like it that way sometimes. I get to do my work and be hands-on and apply things the way that I'm a scientist first. What I have found, though, is that as large as this community of weather people is, whether that's from developers to modelers to operational meteorologists, you start to know people, and NOAA is one of the best ways to do that. And the most powerful thing you can do if you really want to make a difference in atmospheric sciences or ocean sciences or just world science systems is to get to know these people. And so for that reason alone, I think there is at least, and for other people, there will be additional reasons for their personal situations. But for that reason alone, I think that is a incentive to get involved and to seek out opportunities with and adjacent to NOAA, because you're going to find that you're going to encounter these folks. I've got a meeting with someone Amsterdam tomorrow because I happen to be working a midnight shift. And so it's going to be great at 9 a.m. Amsterdam time to have a conversation at 2 a.m. my time. Just how it works out sometimes. But they know of me and trust me and had this conversation through a PhD in Europe because I'm a NOAA representative and because that affords me some degree of connection that I can then use to learn about things and have cool conversations. And it's really one of the best ways that I found so far, having navigated through a pretty serious gauntlet, just like some of you others have, of a career path. I have not made as many connections elsewhere as I have here, at least not as meaningful to me personally as a scientist first. So I think if you are interested in the science and you're interested in atmospheric systems, then NOAA is still a prime place to try to end up for sure.
Fantastic. Thanks, Logan. Go ahead. Please.
I'm Andrea Ray, and I actually am a scientist in a NOAA lab. You didn't get all those. So, and I'm pretty far, I live here in Boulder, and I'm pretty far from headquarters, and I'm kind of at the end of my career and on the verge of going and getting into trouble other places. So if I say something they don't like, screw them. I do want to echo a couple things that people already said, and then I had a couple things I want to say. I'll be fast. NOAA is kind of a family place. You know, it might sound funny to say there's only 12,000 people who work for NOAA, but you know, we funneled in from a couple of hundred grad schools, and we have ended up being in various labs and various meetings and stuff. So you're a couple of degrees of separation from almost anybody in NOAA. And almost anybody, if you pick up the phone and say, hey, I heard about this job, whatever, what do you know about them? Go for it. Say, hey, I met you wherever. Or hey, I used to work with so-and-so, or I went to grad school the same place you did, or any of those kinds of things. So overall, I think it's a pretty friendly place for doing networking. So take advantage of that. AMS is a good place if you can get yourself to AMS and do some of the student things there, but do some of the other things, that's a good thing. Lots of people come into the labs, as a couple of people said, through the cooperative institutes. If you Google NOAA Cooperative Institutes, you'll find a map and a list. They're all over the country, pretty much anywhere we have a science kind of office. There's a cooperative institute here in Boulder. There's one with both with the CSU, Colorado State University and University of Colorado, but there's about 12 or 15 others. You have to go to their sites to look at them, to look for jobs, but you know, maybe there's places you like to live more than others, and certainly some of those focus more on certain science than others. Another thing that's coming up soon is the LaPenta Fellowship, the LaPenta things, and I just checked it for somebody else. They are opening up for next summer. They're opening up in mid-October. So Google LaPenta. They're both undergrad and grad. And there are lots of great opportunities. It also gets you into a network of LaPenta people, and everybody in NOAA knows what LaPenta means. So if you call somebody up and you say, I just did a LaPenta, there's your foot in the door. All right, two final things. One, do you guys have a copy of that opportunity sheet for NOAA careers and students that the education office did? All right, I'll get that to you, and you're going to get it to all of them. Because some of the things like that has, among other things, a list of a bunch of contractors. And so that gets you starting to Google names of contractors and asking people what contractors do, the kinds of things I want to do. And then finally, I want to say, and this is the thing that might get you fired, you probably know that the presidential budget pretty much decimated NOAA research and a bunch of parts of NOAA. But Congress, as a couple of people said, really supports us. And they put some cuts in, but they did a pretty good job of a pretty serious funding for NOAA. So that's, I think, one of the reasons why a bunch of us feel a little less anxious than we did a few months ago. So, but anyway, that's what I wanted to say. Andrea Ray, I'm around for the rest of the weekend. It's not a weekend, is it? It just feels like fun, so, yeah.
Thank you, Andrea. Yeah, please send us that, flyer, I guess, and we can paste it into our notes here, and then these will be shared. Yeah, very, very good. I was going to say, we are going to have a networking session in another 10 minutes to talk about, so, you know, maybe some redundancy, but I would say I was very fortunate to have good mentors, and I think that you probably can echo that as well. You can have some passionate ideas on what you want to change from and to, and so on. My master's advisor at Oregon State had a broad connection with a lot of researchers in Europe, and they just weren't doing the kind of land-atmosphere interaction stuff we wanted to do, and that's how I got involved with some European researchers, and that's why I ended up going to do a PhD in the Netherlands. So Ken Mitchell at EMC, where I worked in NCEP, was a very good mentor for me as well, and I really benefited from that. So, you know, the good mentors, well, even Hendrik here, so, because I worked with him for a number of years, so, Yeah, so there's a lot. And then my PhD advisor in the Netherlands as well was very tied into the community. And I think what Andrea said was relevant. You know, you're not too many steps away from somebody else in NOAA. And I will extend that and say kind of in the Earth system research world, and since I traveled through AMS, get involved, it's straightforward. I won't say it's necessarily easy, but you know, being a student on a particular committee, and there's a lot of committees in AMS, get involved in AMS, and then I got involved in some of the WMO activities early on. So not leadership, but actually doing some interesting work that helped improve our models. So, you know, those are some different pathways, and those are some different things that I found really, really beneficial. So let's see, we've got, we still have a little more time, maybe almost.
I have a comment.
Go.
I would like to make a plug for Jake Karstens here. He does the early career stuff at AMS, so if you're interested in more of how to be involved in early career stuff, you can talk to him. Or I can give you the mic if you want to say something.
Oh, you're in the next section.
I should have checked.
Yeah.
Okay.
Networking, kind of overlap as well. So yeah, okay.
Okay. Question. Yes.
Stay here. Save your thoughts and so on. That was really good. I will say some of the other, the Hollingsworth Scholarship. What's that? Hollingsworth. Yeah. Well, we mentioned the LaPenta interns, but there's also WINGS as well. I forget the acronym, what it stands for, but you know, that's for kind of PhDs.
Your Wings fellow is right by the mic.
Yes, we talked earlier. Do you want to say something?
I have a question, but you can finish your thought.
Oh, no, that was it. I was just saying that there's a lot of different entry points. And so actually don't be afraid to dig, reach out, ask for some guidance, ask for some help. What might I do? And so I really benefited from that. And I think that really helped my career. Go ahead.
Right. So I have some kind of thoughts rattling around in my mind, and I'm going to try to cohere it into a coherent question. But I suppose when it comes to like the third bullet there, traditional career paths, that kind of makes sense to me. It's kind of straightforward how I go and enter, you know, the traditional career paths. But what's really vexing me is the kind of non-traditional career paths, you know, contractors, private companies, et cetera. And I know that they're so important, and they're increasingly important as like NOAA increasingly relies on private companies for their observation systems, et cetera. And I guess I'm just wondering, like, if you have any advice for like getting in, like, basically, how is it? How can I get people to respond to my application? You know, I submit it, and then I never hear anything. And it's not like these are people that I meet at conferences necessarily. These aren't people that I collaborate with. These aren't people that you know, are in academia. And so I'm having a really hard time. First of all, finding the companies, which I've heard a few good suggestions here, the AMS board, and then, I'm sorry.
Andrea, he's pointing at you.
Andrea, you suggested some list, which I would love to hear about afterwards. But I guess, yeah, my question is like, how do I get people to respond to my applications at private companies? Because it doesn't really seem like they listen.
That's the $64 question.
I can answer this one for private companies. You're asking private companies? Oh, show up to their doorstep with donuts. Like seriously, do not do not take no for an answer. Contact the people. Say, you know, I just wanted to talk to you about the job that you had open. Figure out who you talk to, and just sit there until the secretary gives you a meeting. No, seriously, you got to do more because there's so much competition, and you want someone that's hungry. And the squeaky wheel gets the oil, or whatever that saying is. Like seriously, that's what you got to do. My ex had no degree whatsoever, and he is now one of the biggest Merrill Lynch wealth management advisors because he showed up every single day with donuts and bagels until someone gave him an interview. And they're like, if he wants this that bad. And now the people in this room, you guys are all credentialed. How easy will that be if you just put a little effort? Sorry.
Yeah, go ahead, please. Oh, right.
So I was going to mention this when we started the session at 10:30. I spent 15, 16 years in the commercial sector. Now I've only been in government too. So maybe I can help you out here a little bit. First of all, donuts, coffee, soda, especially if you're at a college university, there's a private weather company nearby. Let me tell you, especially when I was on second and third shift, that made an impression. I tell this to my students I talk to in Albany or Oneonta in the Northeast, Linden State. I go to a lot of the smaller schools because I was saying this when I started. A lot of the smaller schools are really good about creating very strong, fundamentally strong meteorologists. Hand you your degree, shake your hand, good luck. And literally 6 months after I had graduated, they were calling me to have me help the next group, even though I was still unemployed. Hence why every year now I go back to Oneonta and talk to the students. This is the first thing I tell them every time. Are you on LinkedIn? You, yeah. Okay, good. Too many aren't. That's your first thing. I know social media has a very ugly bent here. Get on LinkedIn. Connect with people. If you're at these workshops, Mike, myself, these ladies, Logan, anybody, introduce yourself. Ask for a connection. Don't send a blank connection. Say, hey, I saw you speak. I'm interested in this. Have a connection. Then start tapping their networks. I got this job because 3 jobs back, met a man that was Dave Vandenhavel. He was in the Air Force 26 years. He exited, got into commercial weather. He had a connection to another man. 4 years later, started a startup weather company. Me and him did that 6.5 years. This job I didn't apply to. Somebody that knew that man saw my resume that I was looking on LinkedIn, reached out to me on the Friday before 4th of July 2 years ago, says, I want an interview. I thought it was spam. Turned out I had an interview. He has me apply to this job, puts me in front of NOAA Tuesday morning after the 4th. I had an offer that Thursday. It's about who you know. Network, network, network. AMS is great. Workshops are great. Connect to other people. I always say this to my team and other people. If I can help you, maybe I'm not the person, but I might know the person who can. And then, yeah, be persistent. Try to stand out in the crowd, especially in the commercial weather, whether it's the donuts, whether it's going to local events, whether it's showing up at the door saying, hey, I'm just curious, what do you guys do? What is it that you do differently than the National Weather Service? Why is commercial weather important and we just don't use the free stuff? That's a bigger discussion for later. But you've got to stand out and you don't be afraid to network. That's just my 2 cents.
ABH, always be hustling.
I'd like to add something at some point when I can, guys, if that's okay.
Go ahead, Logan.
Yeah, go ahead. Go ahead, Logan.
Sure. I'm going to steal about 2 minutes because this is really important. Because I think that there's a bit of a audience to presenter bias that can happen. And I want people to be aware of it because I've been in the seats before. Most of us have. And you see these people who might be presenting to you and they seem rather outgoing. And they talk about things like networking and getting to know people. And then in your heart of hearts, you're like that's hard. Like, it's hard to talk to people for some of us, especially in a science like this. I mean, it's not unknown that the physical sciences, quantitative sciences in particular, we can be introverted at times. And I'm happiest when I'm alone crunching some numbers or doing some data science. And I know a lot of you probably are too. And so I want to speak to you for just a moment about that. It's how do you actually network? And there's going to be a really good effective ways to network conversation here next. And maybe this will be a good way to get interlude into that. But as an operational meteorologist who is quite introverted myself, but I had to learn how to talk to folks. And one thing I learned, and if anybody would give me like a show of hands, is anyone in this room anything more than just a person? We all are. People on the stage are just people. The people you see on TV are just people. And all of you are just people. Don't be afraid to talk to us. And don't let the intimidation factor. I grew up looking at people on TV and meteorologists and all these famous names. And then I got to know them as I got older. It's crazy. I had the opportunity to work with some of these people that I viewed as heroes. And it wasn't really a letdown, but it was a surprise because they're just folks. Like, they're just people, just like you and I. A lot of our NOAA addresses are first.last@noaa.gov. Mine, you can guess my email address just from that. It's my name, first.last@noaa.gov. And you can send me an email, and I'll be happy to put you in connection. And so my suggestion would be, how do you really get your foot in the door? It is by networking, but you have to kind of learn how to network first. And sometimes the best way to do that is by just finding that first link in the chain that then can plug you into someone else's network and leverage those groups of people in the way that you think will be most effective, because that's how you can, even as an introverted person, you can learn to be that person you need to be in the moment. These are skills that you can learn how to do. You don't have to feel so isolated. So please don't feel like just because there's a stage and you're in seats that there's a separation. We're all in the same community, and that's pretty cool. So do reach out to us. That's the main way, my opinion, how you can really get started is feel like you can do that.
Very good, Logan. Thank you. I'll just maybe close with, or do you want to close?
One second, because I found the two-pager. So the two-pager says Hollings scholarships, pathway programs, educational partnership program. NOAA can actually pay for your education in some cases. Lapenta internships, Chesapeake Bay internships, NOAA Ocean Exploration Explorer in Training Program, Office of Coastal Management Fellowship, Dr. Nancy Foster's Scholarship Program, Knaus, and a few more. This is 2 pages of it, and we will share it to you. Yeah, and on top of that is a link to www.noaa.gov/students. You can remember that. If you hit that, you get 59 opportunities of student opportunities at NOAA.
Fantastic. We're going to do some closing comments. I'll just say, if anything, tenacity, especially listening to Tracy, tenacity, and actually years from now, please give back. Please remember where you came from, what you did, and please give back. Okay, let's go ahead. Last comments. Oh, so yeah, start with Jen.
Yeah, I'll just add, talk to anyone here. We are more than happy to help connect you with people we know if we don't know someone directly. So in your instance, I don't know what companies you're applying to, but guaranteed one of us probably knows someone at one of those companies or had. So just talk to us and we'll help you connect.
I was kind of surprised at how many people resonated with what Logan said about being an introvert. Okay, so when I was little, I used to cry when I would go to school. I am an introvert. So my mom would tell me to just go up to people and even no matter how scared you are, say, "Hi, my name is Tracy, what's your name?" And I started doing it at 5 years old. I still do the exact same thing today. I hyperventilate when I give public talks. I know. See, yeah, I'm weird. But just practice that and it'll open all the doors. Because as soon as a conversation starts, you're fine, right? Like you just need to say, "Hi, my name is, what's your name?"
Yeah, you have to step out of your comfort zone. I am an introvert who has needed to adapt. So, and let's close with Alice.
Yes, thank you. So the last thing is getting your foot in the door. You guys are at this workshop, like your foot is already in the door, like that's kind of whatever. Good job. I feel like the thing I want to leave you with is we all spent so much time, you know, in our school, like getting the degree that we want to get the perfect job that we want. I encourage you guys to go back and, you know, get a whiteboard or get a blank piece of paper and really visualize what you want to be doing every day. Like the things that Logan does every day, I don't want to do. Like you need to decide like how you want to spend your time, and do you want a 9 to 5? Do you want a family? Do you want to, you know, have your 3-day shift? You know, like really think about how you want your future to look, draw a picture of it, like whatever you want to do, and then work backwards to figure out how you can make that happen, rather than just blindly looking at all the jobs and being like, well, I fit that description. It's like, is that really what you want to be doing? So. Yes.
15 years, I've had my fill. I'm doing other things. It's okay for that to change.
Yeah, be adaptable, be dynamic. So anyway, we'll close now. Thanks, everybody. And we're going to be moving over to a networking, how to network, wasn't that it? And a different set of panelists. I guess I'm still the chair. There's going to be perhaps some redundancy because it's, you know, how do you get your foot in the door, and networking is definitely overlapping. So we'll take a minute or so. Thanks, Logan, very much, very much.
It's a pleasure. Thank you, guys. You have a good one.
Let's see, how many of us are there? 1, 2, 3.
We have 2 online.
Oh, 2 online.
Aaron and Sigale are online. So
Okay.
make sure our guy knows that.
Yeah. Do you see 2 people online? You don't have to worry about sitting in the right order or anything like that. I just don't want to drop the mic. I don't want to be that guy. Ah, right. Okay. There. Are they? Okay, we'll give it another minute. Well, so for those of you that joined us, effective ways to network. Previously, we were talking about how to get your foot in the door with NOAA, and there was definitely some overlap in the kind of things you need to do. So I guess this is effective ways to network across maybe the broader Earth system research and operations community. So there's a lot of commonalities. So yes, okay, fantastic. Karimara, we have you, we have Aaron, Sigale. Okay, there we go. Okay, so we're gonna go with some 3-minute presentations to begin with. Thanks the other panelists for the previous session. So we'll move on. Karimar, do you want to go ahead and tell us about what you do?
Hi, I'm really happy to be here. I'm Karimar Ledesma Maldonado. So a little bit of my background, I just did my bachelor degree in theoretical physics with a minor in atmospheric science. And during that time, I did a bunch of summer internships. And one of them, it was a NOAA WPC International DEX. And after doing that internship, I just continued pursuing my studies in the US. So I did 2 master's degrees, one from the University of Nevada in Reno and one from the University of Wisconsin-Madison. And those, like the internship experience and this master's degree that helped me to get the skills that I needed to get the job at the NOAA WPC International Desk later on. So this is something that definitely opened me the doors to discover new opportunities. And also during my time doing my higher education, I also get involved in different committees, from my local department, but also from the AMS. And for example, the committees like planning committee to organize workshop for the summer internship or mentorship program, diversity and inclusion committees, and committees from the AMS like the Board of Student Affairs, Board of Early Career Professionals, or Committee for Hispanic and Latinx Advancement. These communities help me to get involved with not only to get involved with the community, but also to develop another set of skills like organization, leadership, teamwork, communication, and networking. That's really important because that opened you the door to do to discover opportunities like summer internship. For example, my opportunity at NOAA WPC International Desk when I did the summer internship was because I attended to an activity there and they just were looking for a student for that to fill that space. So not only get you opportunity, but also you met fascinating people in the field with a broad experience that you can listen, admire, ask questions, and ask for advice. And also during that, by being involved in committees like that, those ones, you organize activity like workshop that you have the opportunity to meet like a bunch of people there and you listen to their story. That's really important. And that interaction with other people in the field is just like allow me to discover multiple and possible opportunities in this field that you don't know where you're going to end in the future. Like, for example, I did the internship there when I was an undergrad. I didn't have any idea that I was going to end up working there like 10 years later. So for me, this like all just all the opportunities that you can get when you're an undergrad or a grad student are really important, and all the connection that you start building will help. It will. So I'm gonna leave the floor for other speakers now. Thank you.
Yeah, thank you very much. It's very impressive your various AMS groups you're working with. An excellent way to network. So stay online, of course. So we'll move on to Jake.
Yep, sounds good. Thanks, Mike. So Kari just kind of stole my flow about AMS service, and Jason stole my flow about like all the other advice, and Allison stole my flow about being the chair of the early career board. So not sure how to avoid redundancy at this point, but I should say hi first. I'm an assistant professor at the University of North Dakota, so you could probably guess what I study. That's right, tropical cyclones, horribly ironic. Second year there, so I'm kind of actually the poster child for career linearity in a sense, so it's a bit of a divergence from a lot of the people you've heard from over the past hour or so. I've always kind of wanted to be in the academia setting, but I think the reason for that is kind of what I want to emphasize here, and it's kind of about making the most of service activities that you get involved with, just like Kari kind of alluded to. As a student, as a professional, you never stop learning, you never stop meeting new people. In my case, my current position, service is only 8% of my contract, but it's honestly 80% of the fun I have. I like teaching and research too, don't worry. But my why for being a professor is because I want to be that first link in the chain that we talked about earlier. That person that can say, hey, you're coming in with this unique passion, your own story. I want to learn from you and the person that you are and connect you with those people that can get you where you want to go, even if I'm not that person, right? The hurricane researcher living in Grand Forks, North Dakota. There was a conversation too at the end of the last session about kind of paying it forward. And you'll find that as, I think, a very common theme around this field. Something I want to say is that it's actually never too early to do that. One thing I got involved with as an undergrad student that really motivated me toward my eventual path was getting involved in an AMS local chapter. And specifically, my role, I was the vice president of that chapter, and so my job was getting to plan meetings at our end-of-year banquet, and that was a platform for me to actually get to know professionals. There was a position I had that kind of was the kick in the pants to get over that introvertedness and really get to know people and build out a network organically, but also to do that for the people around me. And so something I kind of really stress as I'm the chair-elect now for the Board for Early Career Professionals, so come to that conference. And also volunteer positions are open for AMS boards and committees over the next couple of weeks here, so I'm happy to talk about that. But something I've been saying to our board members, because it can kind of be scary to think, what does a whole society need, right? Especially for our mission, where we're all about supporting the people that are, fresh out of school and getting their career started and navigating all these life changes. Be a little selfish, right? If there's something that you want out of a position that you have, somebody you want to meet, some kind of event you want to put on, there's a good chance it's going to help out a large number of other people too. I kind of feel like we have a little bit of like a decision paralysis of sorts, where we maybe don't know that big perfect thing to do to meet the needs of all 5,000 people that are going to the AMS annual meeting or something like that. But in reality, right, like anything you are motivated, frankly, to do with the limited time that you probably have is going to do a service for much more than yourself. And so I kind of lean into that when I think about networking, and I kind of use that as a way to make it seem a little bit less scary and a little bit more exciting. Because again, you get to do kind of a greater good. So happy to share anything about some of the other stuff that I'm up to. I keep even in the broadcasting world, for example, where I teach a broadcast meteorology class at UND. So I'm kind of all over the place. I actually don't even use any of the UFS models in my own research right now. So consider this an example of, networking. I'm here because I want to meet new people and kind of stay connected with, parts of the field that I don't regularly interact with. So I'll leave it there.
Yeah, fantastic, Jake. That's the don't be afraid to reach out. Sometimes you have to overcome that introvertness, but important. So, and again, these slides will be available. So let's go to Aaron online.
Yes, good afternoon, everyone. I am Aaron Pratt, and I currently work as the Deputy Program Manager for the Joint Technology Transfer Initiative program within the Weather Program Office. A bit of background on me, and I'll try to weave in some nuggets about networking as I go through this. I kind of knew wanted to get into atmospheric science since like the 9th grade or so. I ended up going to North Carolina State, where I got my bachelor's in meteorology, and I was thinking of going there for my master's, but one of my professors was like, nope, you actually should go to a different school. Not that we don't want you here, but it'll be good for you to grow your contacts. You'll still have all your contacts here, but you'll get new experiences and you'll have new people to kind of add to your network if you go away. So I took his advice, went to Penn State for my master's. I met my future doctoral advisor at Penn State and ultimately followed him to Howard University for my doctorate. So I've been at NOAA for a little over 14 years or so, 12 plus of those as a contractor, last couple of years as a federal employee. And honestly, I feel like it's taken me this much time to kind of figure out where I wanted to go career-wise. I initially thought that I would be maybe a researcher in academia, but the actual course of my career, I found out that I've been in positions that were kind of research adjacent or research to operations adjacent. During my time trying to kind of figure out my career and where I should be, I had lots of discussions with friends in the field. I was lucky enough to have folks that I worked with that I could kind of talk to about things outside of, say, my job, because maybe they had different experiences in the field, and they could give me advice on maybe what I should consider. And ultimately, I kind of came to the conclusion that I like being able to kind of help researchers from my position. We fund a lot of research and kind of help researchers and students or whatnot advance research into weather service operations. And so what I want to have is kind of the takeaway from all of that is to never kind of forget the different places where you were, still keep in contact with those former coworkers or former friends that you have from a job, because over the course of your career, they may end up in positions where they can actually help uh, provide an opportunity, or even if not, just kind of talking things through can help you figure out, what you'd like to do and what you'd want to do. I feel like that's really helped me over the course of my career. Of course, I would suggest, and you may hear that from other speakers as well, but just if you can, definitely find a mentor or someone that can mentor you. That's a very important part of your network. That is actually something that I look back and it's something I feel like, maybe I should have done that, better or differently, but definitely take time to, find someone that can mentor you and, keep up with those in the field, your colleagues, because again, they can be super helpful in helping you kind of find out where you want to be, and vice versa. You might be able to help them out as well. So definitely look at it as kind of a two-way street. And okay, I don't want to ramble too long. I know we have limited time, so I will exit stage right.
Thank you, Aaron. Very, very, very good thoughts. So maybe we'll just keep moving on right now, and we'll have our panelists online to continue talking. Sigel, shall take it over.
All right. Good afternoon, good evening. My name is Sigel Thompson, and I'm also in the Weather Program Office. I'll also give a little bit of background, and then I'll leave you with a couple of tips for networking, specifically for mid-career. So I obtained my bachelor's degree in meteorology from Penn State University, and then I went on to get my PhD from Howard University. From there, I took a couple of positions. I did a postdoc at NASA for a couple of years, and I was also a visiting scientist with the DoD, and I even served as an adjunct professor before coming to NOAA. So I started my NOAA career in 2018 as a contractor, and I was supporting the Hurricane Supplemental Program within the Weather Program Office. And that office was formerly known as the Office of Weather and Air Quality. But it wasn't until I received some tips from colleagues and friends in terms of applying for federal positions, the application process, that I was able to secure a position in OAR with the strategic management team. So that particular position, I was coordinating and facilitating OAR scientific laboratory and program reviews. So these two positions were really allowed me to expand my network and meet experts in different areas. And I really was able to gain a broad understanding of OAR, NOAA in general, and OAR. From there, I was asked to serve as the special assistant to the acting deputy assistant administrator for programs and administration, or the DAA, within OAR. And that opened up even more of OAR to me. So I was able to, build my network from these positions. From there, I was also asked to serve as a project and program manager, using those skills that I'd already had to support the acquisition of a major technology. So throughout my career, what I can say is I've been very open to opportunities as they have come up. I definitely had my path, but being open is always helpful. It broadens you, it gives you a different vantage point. So I want to share a few tips specific for mid-career that can help you network. I have one more slide. So if we can go to the next slide.
There you go.
Okay, perfect. So we've talked a lot about being an introvert, and I think there are very different ways you can actually network. But the first thing that I would recommend is that you identify your personal networking style. So how do you do this? I would say ask yourself some questions. What are your strong skill sets? Do you ask really insightful questions? Are you an independent learner? How do you receive feedback? All of these questions can help to curate how you approach networking. So I would definitely identify your personal networking style. I would also say that you should be authentic to yourself, right? You want to be honest and genuine. You want to build honest and genuine connections, because I think that being genuine is important while you're doing networking. I will also say, consider where you want to be and the skills that you need to get there. Take the opportunities that come your way and utilize trainings and shadowing opportunities to grow your skills. Build those connections, make it authentic, and as Erin said, make sure to keep in contact. This is something that I'm still working on, reaching back out to former colleagues or people you've worked with, just to keep those connections going. So I will pause there and turn it over to the next person.
Thank you very much. Very insightful. We'll go on to Ben.
Hey, to advance the slides, is it just the arrow?
Yeah, just the arrow.
Up arrow? Yeah.
No, up or down.
Oh,
down arrow, I think it's that.
Okay.
Oh, you have the clicker?
Oh, it's right here. All right, center button? Yeah. Okay, got it. All right, I just want to start by saying your identity is not your job. You know, we need to take a step back maybe for just a second. Your job is part of your identity. But why are we really doing this networking? What is the goal? Is it to get the better job, work-life balance, connect with a community you're passionate about? So before barreling down, and these are great tips we've heard, take a step back and ask yourself, what's my end goal here? I'm not going to really talk about my background, but 40 plus years in the weather enterprise, most of that in the private sector, most of that in the operational meteorology side of things. But I did want to say that taking that step back will kind of ground you moving forward. Now, I've never done this before. This talk, I took a step back myself and decided to write down all the places I'd worked. And the ones here in green, I'd worked a decade or more. And so that's, you see NOAA on here, but there's a fair amount of private sector. And then in yellow, worked 5 to 10 years. Most of it weather, although the Making It Count, Monster.com, I trained motivational speakers for the Making It Count program, which is a national motivational program for students. But here, 5 to 10 years, you're starting to maybe do the math and going, wait a minute, even if I take the low end here, that's getting over 40 years. And then when we put the 1 to 5 years on there, this took me a while to make the slide. So you got to remember, you've heard from the early career, next two speakers mid-career. This is the old geezer group coming up now. So we're going to have maybe a lot of experience. But and they say, with age comes wisdom. Well, you be the judge if that's really true. But my point here, and I put it at the top, remember the work in networking. And I agree with Jake, the local AMS chapter. I was president of the Central Virginia chapter, and all the ways of keeping in touch with your colleagues, past and present. But I have a little different bit of advice. Work. Nobody knows your skills like they will if you work for them. And what's not up here, by the way, if you really want to make money, stop working for someone else and work for yourself. I haven't listed the businesses that I own up here. But work while you work. Now, within the parameters of what you're allowed to do, I'm not telling you to do anything you're not supposed to. But in my life, my career, I've never worked just one job. Just past Saturday, I forecasted for college football. It's on the weekend, so it doesn't interfere with my NOAA job, right? So keep this in mind that to me, yes, you can network and you can share your skills and your talents and you can tell people, or you can work for them. And this often leads to more and more jobs. And it just almost seems to me, it just has a way of working out. Let me see if I can get this to work. Oh yeah, here we go. Where is it? This job right here, WSFJ-TV, Newark, Ohio. I was executive producer there. Small group of us uncovered fraud and deception that the general manager was doing to the public and to our viewers. If you don't stand up to that, you're complicit with that. So we stood up to that. So we got fired. On my way out, I was being escorted from the building. The phone rang at the desk that I worked there at that TV station. I pick up the phone. It was this station in Richmond, Virginia, offering me a job. That was the last use of that phone at that job. So it has a way of just kind of working out. I look forward to the discussion time. Thank you.
Very good, Ben. Let's move on now. Oh, that's me. And yeah. Well, there's a lot of overlap between the last group, but in terms of networking, I just realized I've been working for more than 40 years in the research to operations and operations to research funnel that I showed, and that's this little guy here. Well, in various university and national weather services, whether that's in the Netherlands or that's in the US, test beds at NCAR, down to forecasting. And all throughout that, I try to be gregarious. I think I consider myself an introvert, but I force myself to step out because I think it's good, because I like friends and so on. And I was just thinking, wait a minute, I started college in 1975, so that's 50 years ago. I haven't been speaking in terms of 50-year periods for a long time, but throughout that, I've made friends. I've made a lot of contacts, and that networking just continues. It keeps going. I had a rather eclectic background. Some of the people I went to college with, they wanted to be a forecaster, and they went out and they've found their forecast offices, and they maybe transferred around the country as one does. But that was a very linear path. I decided to be more, well, non-linear, if you could say that. But I just list academia, NOAA, private sector, WMO, AMS, NCAR. But through that, there's a lot of other connections that I have as well. So because I've forced myself to reach out, you can probably name a university, at least in earth sciences or more specifically meteorology, hydrometeorology, and so on. And I might know somebody there, just because of that networking you get over the years. And yeah, I think what Ben says, you got to decide, who are you? What do you do? I've always just been interested and passionate about Earth system research. Not necessarily being a forecaster. I did do that, and that was really good for me. Midnight shifts were really tough, I guess. Midnight shifts were really tough, but I endured. But then I found some other passions on doing the research, and then other aspects of this. So networking occurs all throughout your career. So one thing you want to do is be kind to people. Don't burn bridges. And you're going to find a lot of like-minded people that really want to help you often. So maybe I'll just leave it at that, and we'll go to Hendrik. So I guess in our community we can just say the word Hendrik, and people know what we're talking about.
So we're coming full circle. We started with early career, then we went to mid-career, then we had two old geezers, and now we're going back to an early career guy. So I deliberately wanted to be last because I wanted to hear what everybody else had to say and sort of link it together a little bit. And so I am not quite as old, I guess, as Mike, because I only have 46 years since I started my college degree. But I put together a list of how I got where I am right now, and gonna link that to what networking did for that. And so, just for the record, it is completely natural for me to be in my job right now because I always wanted to be an architect. And going back to what other people said already, so once again, when you were saying be true to yourself, if I compare my career with Ben's career, we've both been true to ourselves, and therefore we've had very different careers. So Ben, in what you were saying, I recognize a lot of the personality of my wife, and I don't compare it that way, but my wife is a person who always looks for new stuff, always wants to start something. My personality is I'm a finisher, I'm getting it done. And so with that, I don't have a whole slide full of things, but all these things I've finished something and worked through it. And so to link it to having networking and how I got there, it's kind of interesting to look at the list. So what does it mean to be in a weather enterprise? Well, I basically didn't even realize that I was in the weather enterprise, but in 1985, actually in 83, I started working on wave modeling as part of my either a research assistant job or as a PhD student. I didn't realize that it was the weather enterprise because later I figured out that thanks to the Titanic sinking, there was something called the Safety of Life at Sea Convention. And in 1974, the Safety of Life at Sea Convention decided internationally that wind waves and surge on the beach was something that was not an ocean service problem, but a weather service problem. And so that is why I actually already was working for the weather enterprise, or in the weather enterprise at that point. But it goes further back. So I didn't even realize that I had mentors and teachers and network people that formed my life. So I have never had a formal meteorology education. I was educated by my grandpa, who was a farmer, potato farmer, on how to read the sky. I predicted the weather forward, and that became important for me because when I was, even before I went to college, I was a sailing teacher. I was a commercially certified sailing teacher, worked with a sailing school as a 21-year-old. I was in charge of 16 boats, 64 students, 18 teachers. And these guys taught me practical weather. Of course, in that time, our weather forecast weren't that good, so what they taught me to do was you listen to the marine weather forecast in the morning, then you have an idea what's going to happen around 4 or 5 in the afternoon, and then you walk outside, and then I do what my grandpa used to do, just look at the sky, and I know what the weather is going to be for the next few hours. And so these people were really mentors and networkers for me, and I didn't even realize that they were. And then for my PhD for 5 years, I wrote the original WaveWatch, not a 3 after that, just WaveWatch. And what happened there was that I realized fairly early that it was a kind of a weird combination of things, because pretty good technical and scientifically, but the personality, which is kind of opposite to personality of most scientists. In case you haven't noticed, just a secret, I'm actually an extrovert. It happens. But that means that I had opportunities to go to conferences to present my work. And naturally, I like to talk to people. So I got to know a lot of people that way. And by the time my PhD ended, my wife ended school and I wanted to go ended nursing school. We wanted to go abroad for a little while, and I didn't even have to look that much because I had made some contacts with some folks in the small field of wave modeling that knew that I was looking for a place. And Dean Duffy from NASA invited me to do a postdoc at NASA. How many civil engineers end up at NASA? Anyhow, it happened. Pretty normal. And we can go on from that forward, because 5 years later, or 2.5 years later, my postdoc was done. And darn, my wife has a job at Johns Hopkins as a oncology nurse, and she just started a master's in nursing. So I had to look for something to hold me over. Again, I had been focal in my community of wave modelers. I knew a lot of people. And I was thinking about writing some letters of trying to get a job, but I was lucky because there were people at the Weather Service that realized that they needed a new person and it happened to fit. And thanks to the fact that they knew me, they contacted me rather than the other way around. And you can see that I've been all kinds of different things. It's not like I've been a vet all the time. I started as a National Research Council associate at NASA. I was a UCAR visiting scientist. I was a contractor. I actually came into the federal service as a GS-15 branch chief. I have been a center director, and now I am the senior advisor. And so all that stuff is partially based on those first accidental choices about the fact that I was pretty vocal and outreaching as a student. And if you look at it from a bigger perspective, so why have I been relatively successful in my own mind? Because of the fact that I've always been looking for new stuff. My biggest problem, personality-wise, is that I want to finish stuff, but I'm also interested in new stuff. So I have systematically overloaded myself throughout my career, always saying yes to stuff while there was still stuff to be finished. And so be careful if you're a person like that. But with that, it is really important to have a mindset to look for things. So you have passive network, or active networking, talking to people, passive networking, looking around what people are doing and seeing if there's things that are interesting in that. And so if you want to know what I got out of both of those, how many people can say that as part of a weather service job they have been teaching in Nairobi, have been in Fukushima, no, in Japan, to deal with the Japanese government about Fukushima. I've been a Dutch national working for a for-profit contractor at the weather service, the official UF's representative on an expert team for UNESCO. So it's not about whether I'm good or not, stuff like that. How did I get there? Because I have an interest, I know what I want to do, and people know what I'm doing. And so the thing that you need to do first and foremost is to not sit on your work, but present your work wherever you can. That is number one from networking. Number two from networking, something that Sigel was mentioning and others, mentoring is really important. For me personally, it became important in a different way. About 10, 15 years ago, I go like, okay, I really like my career. I really like the science. The one thing I really haven't done yet is much teaching. And I really would like to do that. I got into discussion with my alma mater, almost got back, didn't work out. And then I stepped back and I go like, okay, I am way too traditional in how I think. I do not want to teach just in standing in front of a class. I want to pass on my experience and my knowledge. So since then, I have really focused on being a mentor all over the place. Last year, I spent about 125 hours as part of my job on mentoring people all over the place. That is people in leadership positions all the way to one of my mentees was a GS7 librarian in Boulder here. And so with that, what does that mean for you? Why do I mention that? Well, Mike, stand up for a second. So this is a leader in our field, right? Yeah? Does he look scary? I don't think so. Does he look scary? If you say yes, I should talk to you. So the point is, people like Mike and this others, they are not scary. We like to talk to people, most of us, when we're here. I should stay with the microphone. As a mentor, I have been able to get my mentees to talk to people like Sarah Kapnick, who was the chief scientist of NOAA, and particularly for female mentees who are looking at how do you deal with working as a underrepresented group in there, having a chance to let somebody contact somebody that looks like you.
We only have less than 5 minutes left, so we want to open it up for questions.
I'm almost done. I know I talk too much. But Tracy, she's helped me with that. I've brought people in contact with Tracy. I brought people. Sigel, she was one of my mentees at one point. Yes, Sigel, you should stay in touch with me. Just kidding. So anyhow, be open. Remember that you can do active and passive networking. And we are not scary. We want to hear from you. So talk to the people higher in the organization and take it from there.
Very good. Thank you, Hendrik. Thanks. And I'm not scary. That's right. So let's see. Wave Watch 4 is up. Yes. Okay. We didn't have any list of questions. Well, we have time for some questions. Go ahead. Please.
Okay. Also, I want to mention that our session ends at 4:30, but the next one doesn't start till 5. So if people want to stay, they can stay, or you can leave at exactly 4:30.
Okay.
That's fine.
Do some networking.
Right. Okay, so my question is kind of for Sigel and Ben, but anyone, I guess, could answer. So Sigel talked about being open and kind of taking all the opportunities that come to you, and Ben obviously did a gazillion things. So I'm wondering if you guys have any experience or advice about balancing things, like if you're like attending conferences, or you're applying for jobs, or you want to like start your own business, or you want to publish papers, or you want to train, and it all sounds like a lot, and like you want to, of course, try to do all of these things, but do you have any advice for how you can balance that or prioritize those activities?
Did you want to go first, Sigel?
Sure. Thanks, Ben. Really great question. I was just listening to something. I don't even remember what I was listening to, but they were talking about the definition of priority, right? When you prioritize something, it really should not be priorities. It should be priority, just singular, right? So I would focus on doing one thing at a time, knowing that you can change and you can shift and your career or your path can morph. So I would keep it in terms of, what your trajectory is. You may take, there could be many ways to get to where you want to be. It's really about getting the skills that you need to bring you to the eventual goal, right? So I would look at it as trying to do one thing at a time. I have tons of interests, but it's really important to meet the interest, but then also focus on how you want to get to your journey. Not being afraid to step away from your planned trajectory to take opportunities that could build, but pulling you back to your eventual trajectory.
Very good. Ben.
Yeah, I was just going to add real quick to that. Lean into your passion. This is a passionate group, so lean into that. And one thing I didn't say when I talked about work, the work and networking, is work hard in your job. That'll get you noticed too.
Very good. Oh, Hendrik.
I just want to quote Gail on what she said earlier. You have to know yourself first, and you have to be true to yourself. And there are people like me who take way too much on. You have to know that you are a person like that to be able to avoid it. And there are enough people that I know that are completely different, but we are all different. So know yourself and figure out whether it's an issue for you. If it's an issue for you, actively deal with it.
Yeah, lean into it and don't burn out. That's why you've got to balance things. Go ahead, Jen, you have something.
Yeah, I was just going to ask if I guess it's for anyone, do you find value in finding a mentor that might be completely different than yourself, either personality-wise, job-wise, career-wise, like completely other realm of possibility for a mentor?
Yeah, I can't say a whole lot to that because my mentors that I named, I think are all, similar in terms of what I wanted or what I was used to. So does anybody here in the panel have boy, this mentor that I had was really different, but I learned something. Go ahead, Sigal.
Sorry, was there someone in the room that wanted to speak first? Well, I am definitely an introvert, and as you can see, Hendrik is not. So yes, I found great value in having a mentor that is completely different because it gives me a different perspective on questions that I may have or topics that I want to discuss. I have a completely different perspective. So I think there definitely is value in that. But I also recommend having a number of different mentors. And the mentors will change throughout your career. You can still reach back to them or reach back for information from them or, to give them, just have regular discussion. But I do recommend having multiple mentors.
Yeah, and I just wanted to add to that, my mentor was a chaplain. So it is kind of in the sky. But what I wanted to say though is that mentor helped me through the tough times, because there will be times when maybe you don't have a job or maybe the networking didn't quite work out. For me, faith, family, and friends, you got to have at least 2 of the 3. But my chaplain mentor helped me understand that. Thanks.
Great. Any further questions from the audience? Please don't be afraid to reach out and ask.
Hello. I was just wondering, because you guys were talking a lot about mentors.
Do you want to introduce yourself?
Oh, yes. Hi, my name is Anna Maria, and I'm a grad student at UCSD. But yeah, so since you guys are talking about mentors a lot and how your mentors can change at different stages in your life, I guess, how do you go about finding one and then making that connection?
One minute.
So very simple. during my career, I have made my supervisors, I forced them into becoming my mentors. And I do that by, whenever I do performance reviews with my supervisors, I am not satisfied with hearing what I'm doing wrong. I want to hear from them how I can do it better, what I can do better. And so being proactive with the people that are your bosses is a really easy, quick way of forcing people into becoming your mentor. And it helps you also in terms of if you need a reference later and all that kind of good stuff. But that is a really simple, practical way. And recognize people that are potential mentors of opportunity.
Anything else that anybody online or in the panel want to say? Oh, well, you can start with Jake, and then yeah, sure. Karimar, you can go next. Why don't you go ahead?
Sure. This might be a little bit out of left field, but I agree with everything that Hendrik just said. But you can be your own mentor in a sense too. I think there's a lot of power in just being present with every experience that you go through. And that is regardless of where you are at in your career. I try to not generalize these statements to just the students in the crowd, right? We're all kind of students of the game in a sense. We're always learning new things about ourselves and about, of course, the field that we all study. But I think there's a power in, like, for example, in the academia world, right? We oftentimes kind of tell prospective grad students, oh, you're applying for the PI or the project or whatever, but there's so much more about what makes a graduate need to pay attention to, and there's so much of those soft factors that are a part of who you are. And so, of course, finding the people in your network is something that we're all here to have that conversation about, and I'm happy to be someone you can talk to personally. But I think there's also a lot of power in just taking a step back after every one of these experiences that you have and just say, sure, the particular topic that you're studying is a thing, but is the process, is the environment, is the team that you're a part of, are those the things also that, bring you joy in what it is that you're doing? I just think there's value in that on top of everything that's already been suggested. So go ahead, Kari, sorry.
Okay, yeah, Kari, go ahead.
Okay, hi. So I have like two maybe idea or examples. For example, the ones that I used when I was an undergrad was to send an email to a professor or someone that, hey, I would like to talk about this topic, or I have doubts about what to do for my career or something. Just a very short email. Like, can we just meet for a coffee or something very short, just to set up a meeting, like very short meeting, like 30 minutes meeting. And most of the time they just say yes, and you just go there and just talk with them and just building with that connection. I know that first can be awkward or weird, could be like, especially if you're an introvert like me, but it's something that you just take time, that you just keep saying like, hey, can we just meet again, maybe just to have a follow-up and just to see what are the next steps to do. That's, I will say, maybe the one idea to do it. And another one is just like some programs, at least in the department at University of Wisconsin in Madison, they have a mentorship program. I don't know if the other university or departments have that mentorship program, but I know that AMS also have one mentorship program, and that you can like, I don't remember exactly the details how to get in contact with that, but I know that it exists, and you can just submit your like request that I want to be involved or participate in this mentorship program. I would like to have a mentor. And in that way, they will find a match for you, or who's the person that perfectly like match your interests, that can help you to give you the guidance that you're looking for. I know, for example, now I remember the private sector, the AMS private sector like committee, they specifically have a committee for that, and you can send like an email to the lead of that committee, and I remember which are the days or times that they're open the floor to receive applications or people that are interested, but definitely they have a mentorship program on that committee. So those are different like methods that you can reach out, or different ideas that can help you to find that mentorship that you're looking for. Especially, and you have to be clear when you're participating in this mentorship program, like about your interests, what are you looking for, and what you're going to take out from this like relationship or partnership or mentorship, mentor-mentee relationship. So I don't know if anyone have more ideas, but yeah.
Yeah, thank you very much. Any final questions from the audience? Okay, well, maybe we can have a closing comment, unless we've covered everything. Actually, about mentors, I would say some of it can be very organic. It just happens. So be looking out for it. There might be somebody. It could be a supervisor. It just could be a colleague, some other, some other researcher, scientist, whatever in your group can be mentors as well. And go ahead, Andrea.
Can I just mention something really quick? There was a sign-in sheet floating around. If you haven't signed it, please find it, because it'll have your emails, and we can share all of this information with you all through email. So
Yeah,
just want to
that's the first step.
I just wanted to jump on what Tracy was saying about how do you start these conversations? Yeah, you start with, hi, I'm Tracy, or hi, I'm Andrea, what, your next team. But
Yeah.
somebody also just said it. Say, when you're going, you're expecting, and this is from a person who is not as extroverted as most people think I am, but especially early in my career, I would have something I wanted to talk to somebody about. I would have looked, especially if there was somebody in particular I wanted to talk to, I would have looked up a little bit. It's so easy now that you can actually do this Google thing on the web. Like at the beginning of my career, you couldn't do that. Hey, I'd like to talk to you about X. Or, hey, I'm working on a project about Y, and I think it's something related to what you're doing. Or, hey, we both, as I said earlier, we both went to whatever grad school. What did you work on? Things like that. But just, it's really easy. And then realize that often the person on the other side is perhaps not, even though we're all friendly and not scary, is maybe not as comfortable or thinks that having conversations out in a coffee room is awkward as well. So just be normal and have something to talk about. So
Yeah.
just wanted to throw out how to get it started.
Yeah. A lot of different personality types. How do we negotiate that? Absolutely. Well, anything final to say, Jen? Okay. I want to thank Kari, Aaron, and Sgail online. Thank you very much for participating. And of course, Ben, Jake, and Hendrik in the room. Okay, thank you. And Mike. Well, anyway, thank you very much, and it's been great to talk with you.
Actually, Mike, if you would stay here for a second. First of all, we're a little over, but I think that was worth the time. Again, we can stay in the room and continue networking, but this is the end of the session. I want to thank all the speakers, all the chairs, the organizers. Thank you all so much. A hand of applause for all of them. I also want to give very special recognition to both Mike and Ben here. They are transitioning and retiring here very shortly. They're not leaving us completely. They're going to transition into new roles. I've enjoyed getting to know both these gentlemen the last couple years. I've seen you guys at a couple shows. Mainly we talk over email and video, but it's been an honor to work with you, to learn from you, and I know that will only continue going forward. Please give a round of applause to both these gentlemen for all their careers and their work to the field. One last thing, I would not be doing my job if I didn't mention this in terms of networking. STI, my group, we do workshops all the time. Next month, we have the air quality workshop we'll be hosting in College Park, Maryland. In-person registration is closed. Virtual is still available. Dates are October 16th to 17th. We'd love to have you involved. HVIB Annual coming up tentatively the second week of December. Registration for that will be coming up soon. We'd love to have you involved in that. And then I can say this, probably spring, April, May of next year, we'll be doing the second S2S SFS conference or workshop, probably also in College Park, Maryland. Be looking for that. Again, you can follow us on LinkedIn, follow us on our page, connect with us. We want you to be involved, present, continue the conversations. And the last job I have, I believe I'm supposed to choose a raffle winner. At least that's what my instructions say.
Is it
And Jacob, I'm sorry if I took a lot of your thunder earlier. I apologize. And I already connected with him on LinkedIn while he was sitting up here, by the way. That's why I have a link tree. Yep. Check that link. Like as you said, when you go to connect, read that resume, read that CV, find a way to connect.
You can just read mine.
Well, if we're going to do that, I'm just going to read mine, guys. I mean, I don't even know what the prize is. It's a fellowship or position at NCAR. I'm very interested. Look, you gotta, you know. I should probably tell my chair. Look, you gotta sell yourself, folks. You do what you gotta do. How
do you do this, Ralph?
I don't know. All it says in my instructions is Allison will bring a bucket. Jason will choose a number.
I think pretty sure that Jen is getting the bucket.
Okay. While we wait for the bucket, any last minute questions or thoughts from anybody, please? Or is everybody just ready to go get, stretch their legs? All right, here she comes.
I don't know if this is going to work because it's like everyone's number.
Oh, I thought maybe, well, this is going to be fun. So why does it say in my instructions, Jason will choose? I just got lucky? All right, well, if it's not in this room, it'll go to...
It'll happen.
All right, blind test. All right.
Everyone have the raffle ticket out?
I've got one in my hand, 503, 505.
It'd be awesome if it was the first person. I was going to say, you might want to go through quicker.
Yeah, I dropped one on the floor. This is the next one. 355.
All right.
Darn it. Third one, 374. This might take a while longer than we thought. 354.
We just pick randomly from the sign-in sheet.
361.
Did you have 354? Okay.
All right, 561.
Oh no, we're one off.
541.
It was like we're close. We're one number off.
377. No, I didn't. 563. 363. I'm getting very close to doing that. I'm going to do one more, and then maybe I'm going to say the sign-in sheet. 569. Come on.
Hey!
All right, we got one. I think it was the 10th one.
Good job.
All right, and I believe that is the end. Again, thank you all, everybody. We'll see you in the other sessions the next couple days.
Thank you very much for being the main chair.
Yeah,